Check.
Yeah, so he was like this, talking to going in.
Check, check, check. 1, 2. 1, 2. Check, check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's impressive. And almost no delay at all. That's nice. Yeah. Check, check. 1, 2. And I can hear myself pretty good. 2. Stay there. Yep. Check 1, 2. Free birds.
Check, check. Good morning, Harry. State your birthday. I heard. Good morning. That's where he knows.
Wow. Yeah, scholarship. What technology is kind of enough? I think that's. Yeah. Yeah, yeah. Yeah. Right here. She actually does. Yeah, yeah. So, yeah, there's actually a scene. Yes. But yes, yeah. Oh, yeah. Yeah. At least I my dad.
Oh, Charlie. John. John, just want to give you a heads up. This one's live right now.
All right, folks. Thanks for making it over from coffee. We did have coffee turned on earlier today than yesterday, so I hope that helped get people caffeinated. We're waiting just a second. Our keynote speaker for today is on Zoom, and he is logging in as we speak. Once he's sure to be online, we'll go ahead and get started with the formal announcements. It'll be just a second. Oh, you used all your paper. Good. We can do that. So Doug, I'll delegate somebody. So there's Yeah, there's a notepad right there on the end of the table. At least there used to be. Yeah. Use that one up if that gets used up.
Take the microphone, make sure they give us a credit card number nice and loud.
Yeah. You're good. Okay.
Hello.
All right, everybody. Shh. Great. Our keynote speaker's online, which is what we were waiting for, so we're ready to go. Should be briefer announcement today. You'll hear some of the same things you heard yesterday, but we're going to skip a lot of it. But first, I do want to have Doug Loss, our chairman, come up and thank our patrons. So, Doug, the lectern, or you can use this one, your choice.
Good morning. I hope you're all awake. As we did yesterday, I want to thank all of the patrons who have helped us make this possible with their financial, organizational, and other contributions. Those patrons are the University of Arizona, the Limitless Space Institute, Pima County Economic Development, the Breakthrough Initiative, Ban Books, AGM Precision Machining, and the individuals Rob Hampson and Joe Meany, Arizona Technology Council, Boost Phase, Broder Partners, Nexolve, Phantom Space Corporation, and individually Ken Roy and Martha Knowles. Visit Tucson, Chris Mooney Photography, and individually James Early, Henry Kate, Thomas Wickland, and Philip Lubin. These are folks who, without their assistance, we wouldn't be doing this. So if you have any business that you might be able to throw to them, consider it.
Thanks, Doug. Appreciate it. All right, a few quick announcements. I'd announced yesterday we're doing these Birds of a Feather dinner on Monday evening for those who are sticking around, where any of you can choose a topic and a restaurant nearby, or not nearby, choose a topic and a restaurant and host a dinner at everyone's individual expense. So we're not paying for this. But just if you want to talk about propulsion, if you want to talk about life support, and you want people like you to cluster around and have a dinner, that's something we're doing on Monday. And there are sign-up sheets out at the registration desk where you just, if you want to create one, just create one. This is completely self-organized. I had a question yesterday, well, why aren't we doing those on Sunday night, which is today? And I said, I don't know, because I didn't put it on the schedule, but that's a good idea. So if y'all are interested in doing one tonight, if you're leaving early tomorrow and not going to be around for Monday evening, knock yourselves out, grab one of the clipboards, fill something in, and make that happen. That'd be great. I lost the screen with my list on it. Les Johnson, first, for those of you who know Les Johnson, this is the first one of these he has missed, and he's distressed about it. It's the whole COVID pandemic travel thing that makes it difficult for people to travel. We've seen that before. But Les, A, wanted me to apologize for him for not being here, but B, wanted me to remind all of the presenters of papers here at the podium and all of the poster presenters that if you're interested in being in the special issue of Acta Astronautica that he is editing, his deadline is October 1st. And somehow October 1st is next week. I don't know how that happened, but the deadline for that is next week, so he's encouraging you to do that. So we're going to go ahead and get started with our second keynote with Avi Loeb. Avi is, I think, well known to everybody in this audience at Harvard, has written many books. He was going to be an anchor of our author panel this evening. We are doing a science fiction, science fact author panel at 6 o'clock, open to the public, and I hope that most of you come because I'd like you to be here for it. He would have been an anchor of that, but like so many of the people we've run into this weekend, Avi was not able to travel, but he has agreed to appear via Zoom. He's logged in. Avi, we've got your slides. We just do this the old-fashioned way, say next slide, and Charlie will punch the button for us. So with that, Avi, if you're online, I'll hand it over to you.
Thank you so much. It's great to be with you virtually. I wish I could have joined you in Tucson. What I'll describe today focuses on the book that I published about 7 months ago called Extraterrestrial. You can see it in the middle of this slide. And if I had to summarize it with one sentence, I would say, when you're not ready to find exceptional things, you will never discover them. A couple of months ago, I published the second book on the search for life in the universe. And it's primarily a textbook about 1,000 pages long that I wrote with my former postdoc, Manasvi Lingam, called Life in the Cosmos. And it's intended for scientists planning to work on this very exciting frontier. What you see on the left side is a photograph that was taken by Herlinde Quilbel, a German photographer, in an exhibit that she had at the Berlin Brandenburg Academy of Science and Humanities. And she came to my office a couple of years ago and asked me to write on the palm of my hand the question that I regard as most fundamental in science. And I said, are we alone? Next, please. So one of the remarkable facts that we've learned recently, relatively recently, from the Kepler satellite data is that a substantial fraction of order 1/2 of all sun-like stars host an Earth-sized planet roughly at the same separation as the Earth is from the sun. And that implies that not only we are not at the center of the universe, as we thought early on, and the ancient Greek philosopher Aristotle argued that, and people believed him for 1,000 years because it flattered their ego. Not only we are not at the center of stage, but moreover, what we find in our backyard is not special. And so whenever we thought that we are unique, that turned out to be wrong. And I think that's an arrogant point of view to think that the play is about us. There are more habitable Earths in the observable volume of the universe than grains of sand on all beaches on Earth. Next. And that brings a sense of cosmic modesty. And when you look at a painting like the one depicted in this slide of an emperor that conquered a piece of land here on Earth, that is a very narrow-minded point of view to be arrogant and very proud of yourself. Next, please. Because that's not very different than an ant hugging a single grain of sand on the landscape of a huge beach. Next. Next. But I can understand where it's coming from. My daughters, when they were young, they tended to think that they are the smartest in the universe, that they are very special and unique. And that's because they compared themselves only to the family members when they were at home. But when we took them to the kindergarten, they got a better perspective. They found other kids that might be smarter than they are. Next. And our civilization will mature by finding others. Next. Now, most stars formed billions of years before the sun. We know that by observing the star formation history of the universe. You see that on the top right. Next. And since I mentioned that a substantial fraction of sun-like stars have a habitable Earth-like planet, next, then we can imagine many of these stars that predated us that could have had life as we know it here on Earth, and perhaps even one of them was as advanced as we are or more advanced as we are. That's sufficient for them to send artificial intelligence systems into space. And AI systems are currently driving cars, and in the near future, they will make medical decisions, and they can behave autonomously, sort of like technological kids that we educate early on using machine learning, and then we can let them explore the world, just like kids. And you can imagine another civilization slightly more advanced than we are that did that, sent such systems into space 1 billion years ago. Next. And if you equip these systems with 3D printing, they could fix any damaged parts and they could reproduce themselves. They can produce copies, just like von Neumann imagined. And over 1 billion years, they can populate all the habitable planets in the Milky Way galaxy, including the solar system. Now, this is not a philosophical issue that we should debate about. The way to find out whether we live in such a reality is to look at the sky and search for equipment that was sent by other civilizations that predated us. That's all. And we should not repeat the mistake that philosophers made 4 centuries ago when they didn't want to look through Galileo's telescope and argue that they know that the sun moves around the earth. When you look at the sky, you see the sun moving. Therefore, it was very natural for them to believe that we are at the center of stage, so to speak. But they put Galileo in house arrest. Today, they would have canceled him on social media. But that didn't change the fact that the earth moves around the sun, and we use that fact when we design space missions nowadays. So the fact that it was not popular back then didn't change anything. You know, humans can decide to be ignorant forever. We can decide not to look through our windows and argue that we have no neighbors, that we are the smartest, and ridicule on social media anyone that discusses this possibility. But that will not get rid of our neighbors. Next, please. So in July, I announced the Galileo project following a visit by several multi-billionaires to the porch of my home when they asked me questions about my book, and altogether provided me with about $2 million in research funds. And I decided to allocate them to this purpose of searching for objects near Earth that may be technological equipment from interstellar space. Because extraordinary conservatism leads to extraordinary ignorance. We should have learned that lesson because of the experience that Galileo had 4 centuries ago, but apparently we haven't. Just a few months ago, there was an article in Nature Astronomy magazine by a philosopher arguing that an unusual object that appeared near Earth, Oumuamua, that I'll describe in a few minutes, must have been natural based on philosophical reasoning. And I thought to myself, haven't we learned something? We need to dare to look through telescopes for the answers. And you can find more details about the Galileo project on the website provided in the middle of this slide. Next, please. So the Galileo project aims to study 2 types of objects. One is objects that arrive into the solar system from interstellar space, similar to Oumuamua that was discovered in 2017. And the other are objects that hover just above Earth in the Earth's atmosphere. Next. And the amazing thing is that, you know, an emitter-sized telescope that you can purchase on the web, you can add it to your bag for $500,000, turns out, that can obtain a megapixel image of a human-sized object at a distance of 1 mile. And that allows you to see the head of a pin on the surface of such an object. Again, it's not a philosophical discussion. It's a matter of getting a megapixel image. And then you can tell the difference between a label saying made by exoplanet X rather than made in China or made in Russia. It's simple. So one objective of the Galileo project is to obtain high-resolution images and monitor objects whose nature is not clear near Earth, in the Earth's atmosphere. These are called unidentified aerial phenomena, UAP. Next, please. And then the second component is to search for interstellar objects, objects that enter the solar system, arrive to the vicinity of Earth, and do not look like a comet or an asteroid. Next. And of course, for them as well, we would like to get a high-resolution image. Next. So you can, there is a website, a web link for anyone interested in supporting this project. And we have some significant level of donations from private citizens. And I got thousands of emails from interested people that wanted to contribute from their expertise to the project. By now, we have about 70 people involved in the project, and it's going extremely well. I must say, over a period of a couple of months, we are already selecting instruments and starting to test them. Next. And of course, this project was inaugurated about a month after the intelligence agencies delivered a report to Congress suggesting that there are aerial phenomena that are not identified, UAP. Next. And this is not a subject that the most conservative organization, the government, has to resolve. I mean, it's quite remarkable that the intelligence agencies admit that they are not doing their job. They cannot figure out the nature of objects hovering in the sky above the US. But at that point, it should not be the talking points of politicians or military personnel. It should go into the realm of mainstream science, where scientists should resolve the nature of these objects. And there were 143 of them reported. There must have been many more seen because of the stigma that there is on this subject. Next. And very reliable people, former CIA directors, Brennan and Woolsey, former President Obama, spoke about it as a serious matter. So the scientists should figure it out. Next. And that's what the Galileo project is all about. Next. Now, the big picture is that it's not clear whether we would survive for more than a few centuries. And of course, currently all our eggs are in one basket. But we should think about spreading them. And I call that Noah's spaceship, because you're all familiar with Noah's Ark, the biblical story where Noah tried to save animals from the great flood. There are many risks here on Earth, and we might want to save life forms that we care about from those. The only person whose remains left Earth is Clyde Tombaugh, whose ashes were put on the New Horizons mission. And actually, one of the members of the Galileo project was the principal investigator of New Horizons, Alan Stern. And I actually asked him, I said, it doesn't make much sense to put ashes of a person you want to celebrate on a spacecraft, because what are ashes? They are just burnt up DNA. It's as if you took the genetic information of a person and burned it up, so there is nothing left. It's no different than the ashes of a cigarette. But if NASA wanted to celebrate a person, they should have put the genetic code in electronic form so that someone finding that spacecraft will be able to reconstruct Clyde Tombaugh. Next. So we know that Earth is our home, but only for a short while. Next. Because of internal threats, there is a risk of climate change, wars, and other catastrophes that are self-inflicted. And there are also external threats. We know that 66 million years ago, there was a giant rock the size of Manhattan Island that hit the ground and tarnished the ego trip of the dinosaurs back then. So there are all kinds of threats. Next. And we should go to space. And let me just say a few words about myself. I started actually on a farm in Israel 59 years ago. 1962 is the year I was born. You can see me at age 7 on the top left. I used to collect eggs every afternoon. I should say one thing led to another. And then in May 2015, Pete Warden and Yuri Milner, actually Pete is attending the conference, came to visit the Center for Astrophysics. And Yuri sat on the sofa in my office in front of me and asked me whether I'm willing to lead a project to visit the nearest star system, Alpha Centauri. And I immediately recognized it's 4 light years away, so it takes light 4 years to make the distance, and therefore you need a spacecraft moving. If we want to do it during our lifetime, it needs to move at around 1/5 of the speed of light in order to get there in 20 years. And that's 1,000 times faster than chemical rockets. And that's a huge leap. In April 2016, we announced the project in New York City in the company of Stephen Hawking and Freeman Dyson. Next. So this is an artist's illustration of the solar system, which goes halfway to the nearest star, which is Proxima Centauri in a 3-star system, the Alpha Centauri system. And the Oort cloud is just the building blocks left over from the construction project of the planets. These are icy rocks going halfway to the nearest star. So if any star has an Oort cloud, they are very densely packed throughout interstellar space. And it's easy for us to lose bricks from the Oort cloud. Next. Now, the nearest star, Proxima Centauri, has a planet. The star is only 12% of the mass of the sun, so it emits mostly infrared light. It's a dwarf star with half the surface temperature of the sun. This planet is 20 times closer to the star, but it happens to be in the habitable zone, roughly with a similar surface temperature as the Earth has on its day side. Turns out that it's tidally locked, so it shows the same face to the star, and there is a permanent day side and a permanent night side as it moves every 11 days around the star. And my daughters say that if we ever go there, they want to live on the strip that separates the day side from the night side. That's where you can sit on the porch and see the sunset forever. Next. And I asked students in my class at Harvard if they know of any animal that has infrared vision that would enjoy the light coming from Proxima Centauri on the day side. And one of them found a shrimp that has eyes that look like ping pong balls connected with cords to the head of the shrimp. And she said, it looks like an alien to me. Next. So how do we get there? That's the Starshot initiative. And the idea is to push a light sail with a very powerful laser beam and connect electronics to the light sail. Next. So this is a quick video that shows the concept. A lot of small, low power lasers combine their beams to make a very powerful 100 gigawatt laser beam. And if it shines on a sail that weighs a few grams, then within a few minutes, it can push it to a fifth of the speed of light. And the sail size is roughly the height of a person. That acceleration, this launch, goes for a few minutes across a distance that is 5 times the distance to the moon. And then after that, there is a journey of 20 years to Proxima Centauri. And of course, the hope is that we get there and the camera on board would take a photograph of this habitable planet and inform us whether it has life on it from a close-up passage. And it takes the photograph signal 4 years to reach us from that distance. So altogether 24 years, you need a lot of patience. You know, humans were not selected by Darwinian evolution to make interstellar travel. I think we should only think in the context of equipment as far as what we send far out. And of course, other civilizations may have done the same. We shouldn't expect contact with living organisms. Next. And there is also a natural way for launching a sail close to the speed of light, and that's by parking it about 100 times the Earth-Sun separation from a massive star that is about to explode. And when a star goes supernova, there is a flash of light. And I calculated that it could carry a sail of the type used in Starshot near the speed of light. The situation is similar to those surfers on the beaches of Hawaii waiting for a giant wave to carry them, except here it's a flash of light doing it. And another metaphor is dandelion seeds that you can see on the right-hand side. Next. Now, we're probably not the sharpest cookies in the jar of the Milky Way galaxy. And by that, I mean, we're not the most intelligent civilization that ever existed. And the reason I say that is by looking at the news. I define an intelligent culture as a civilization that follows the guiding principles of science, which are cooperation and sharing of evidence-based knowledge. And you can easily tell by reading the news that we don't share much, we don't cooperate much. And moreover, a lot of what we do is not based on evidence. Next. So if I had to guess, I would say there was probably a smartest kid on our block. Next. But without prejudice, we should be open-minded and search. Next. And the best place to start the search is in our backyard. Next. Next. And the first object discovered from outside the solar system in our vicinity was found in October 2017 by the Pan-STAR survey on the summit of Haleakala Mountain in Maui, Hawaii. It was given the name Oumuamua, which means a scout in the Hawaiian language. You can see it circled in blue here on the background of stars that are moving relative to it. Next. And it started actually from a very special frame of reference, the so-called local standard of rest. That's the frame that you get to when you average over all the motions of all stars in the vicinity of the sun, sort of like the local galactic parking lot. And Oumuamua was at rest in that frame. Only 1 in 500 stars is so much at rest as Oumuamua was initially. Next. And of course, the sun gave it a kick gravitationally. Next. And as it was tumbling every 8 hours, the amount of sunlight reflected from it changed by a factor of 10. And that implied that it has a very extreme shape. Next. The best fit to the variation of reflected sunlight was that of a disk-like object, pancake-like. In these two plots, you can see a comparison between a disk shape and a cigar shape. And in both cases, the object had to be at least 10 times longer than it is wide because of the variations in the light curve. And a dark color implies a high probability. So on the left, you can see that for many different choices of the orientation, you get good agreement with the light curve, whereas for the cigar-shaped case on the right-hand side, only very fine-tuned set of parameters allow a cigar-shaped object to describe the data. So at the 90% confidence, it was most likely pancake-like. Next. And when the Spitzer Space Telescope looked at this object, it found nothing. You can see it on the top right image. There is no detection whatsoever of anything coming from the direction of Oumuamua. And that implied very tight limits on carbon-based molecules or dust around it. Not only we couldn't see a cometary tail, but also the amount of any evaporated carbon-based molecules was very tightly constrained, and it couldn't be a comet, definitely not a comet of the type that we have seen in the solar system. Even though that was the favorite interpretation when Oumuamua was discovered. People said it's a comet because most of the objects in the Oort cloud would appear as comets. And that's the place where you expect rocks from other stars to come from. But it was definitely not a comet of the type that we see from the Oort cloud. Definitely not. And then it exhibited a non-gravitational acceleration, a push away from the sun. That was a Nature paper. And we actually analyzed the same data with my postdoc, and we confirmed their conclusions. It looked as if there is a force pushing this object that declined smoothly, inversely with distance squared. And no jitter, no cutoff at the ice sublimation distance, as you expect from the rocket effect, from evaporation. So it looked as if, to me, the only explanation that sounds plausible is that it's the reflection of sunlight that is pushing the object. And for that, the object had to be very thin. And nature doesn't make thin objects. So we wrote a paper where we suggested that maybe it's artificial in origin. Next. And that is really the fundamental question. Is Oumuamua natural or artificial? Next. And in September 2020, after I finished writing my book, the Pan-STAR telescope discovered another object that exhibited an excess push away from the sun with no cometary tail. Next. And that was given the name, the astronomical name 2020 SO. No cometary tail implied that maybe it's an asteroid. That's what the astronomers thought initially. But then a few weeks later, next, they found that no, it's actually, if you track the orbit back in time, it came from Earth. Next. And moreover, it's actually a rocket booster that was launched in 1966 as part of the lunar lander mission then. And that's why it was pushed by reflecting sunlight, because it had very thin walls. It had a large area for its mass. Next. And as a result, it behaved similarly to Oumuamua. So we know that this object is artificial in origin because we produced it. It was not produced to be a light sail. It just had thin walls. And I'm not saying that Oumuamua necessarily is a light sail. It may have been just thin for a different purpose. Next. So what are the anomalies of Oumuamua? Next. First, it was not expected to be found. I wrote the first paper forecasting how many rocks we expect from other stars. In 2009, we wrote this paper with Amaya Morrow-Martin and Ed Turner, and we didn't expect Pan-STARRS to find any. And by not finding any, I mean by 2 to 8 orders of magnitude, too few for Pan-STARRS to find any. So there is a huge gap between what you expect based on what we know about the solar system and the discovery of Oumuamua. That was a surprise. That's why I was interested in it in 2017. It also originated from the local standard of rest. Only 1 in 500 stars originate from that system. Its brightness changed by a factor of 10 as it was spinning. It had a very extreme shape. Next. Most likely pancake-like. Next. And then the Spitzer Space Telescope didn't detect any infrared emission from it. Next. So it was small and relatively shiny, but most importantly, it deviated from a Keplerian orbit. Next. And to me, that implied that it's being pushed by sunlight, and therefore it's very thin. Next. Now, most people just said, most astronomers just said, oh, it's natural, business as usual. But some astronomers tried to explain, and I should remind everyone, these are observed facts through telescopes. There is no doubt that these facts were observed, so we need to explain them. You can't just ignore them and say business as usual. Next. So the people that attended to these facts found several explanations. For example, maybe it's a cloud of dust particles, 100 times less dense than air, very porous, so that it's just like a feather and it's being pushed by reflecting sunlight. The problem with that is such a cloud 100 times less dense than air will not maintain its integrity when it's heated by hundreds of degrees and gets close to the sun. Next. Then next, there was a suggestion, maybe it's an iceberg of molecular hydrogen, so that we can't see the evaporation because hydrogen is transparent. And the problem with that, well, first, we never saw a hydrogen iceberg. We don't know if it's made in molecular clouds. But moreover, such an object would evaporate very quickly within a few million years and wouldn't survive the journey through interstellar space. Next. Then there was a suggestion, maybe it's a nitrogen iceberg chipped off a surface of a planet like Pluto around another star. The problem here is the mass budget. We showed in a paper that there is just not enough nitrogen in all the stars of the Milky Way galaxy. Next. So let me just illustrate with a few numbers. These are 2 papers that I co-authored with younger people. One showed that the hydrogen iceberg would get evaporated in a few million years. That's shown on the left, the evaporation timescale versus size. The other one showed that the nitrogen iceberg would get evaporated in less than 500 million years. That's the characteristic lifetime that was assigned to such an iceberg by the original authors of the paper. For that to be the case, so that it survives 500 million years, you need the initial size to be more than 10 kilometers. and it will end up in the size of 100 meters or so. So 99% of its size would get completely evaporated. Then you have a huge problem with the mass budget, huge problem. There is just not enough nitrogen. Next. And even if you didn't take this, even if you assume that the evaporation is not substantial, still you need more mass in exoplutos than you have in stars, basically, in order to make enough of those chips that would account for Oumuamua. And anyone interested in the details can look at the archive. Next. So my point is simple. If it's something we have never seen before, we might as well also consider the possibility that it's artificial in origin. Why ridicule that possibility? And this is a paper from the 25th of August, posted on the archive, co-authored by people that proposed the hydrogen iceberg model. And in the middle of the abstract, I highlighted in gray here, you can see the sentence saying that the hydrogen and nitrogen models have serious difficulties. That's not me, that's the people that proposed this model. Next. So as far as I'm concerned, when you walk on the beach, most of the time you see rocks that were naturally produced. These are the comets and asteroids that we have seen many times over and over again. Next. But every now and then you see a plastic bottle. Next. And that could be Oumuamua. Next. Next. Now, if you imagine a caveman finding a cell phone, the caveman that is used to playing with rocks all of his life would argue, oh, the cell phone is just a rock of a type that I've never seen before. Just like saying Oumuamua is a rock of a type that we have never seen before. A hydrogen iceberg, a nitrogen iceberg. We don't know if such rocks are common, if they could explain the first object we see, but it's something we've never seen before, and that's it. And of course, that's the beginning of a learning experience. Because if the caveman presses a button on this shiny rock, he would record his voice. And if he presses another button, he would record his image, at which point it will be clear that it's not a rock, it's something else. Next. Now, there was an interstellar object that looked like a comet. It was the second one discovered. Next. Called Borisov, because it was discovered by Gennady Borisov, an amateur Russian astronomer, and it looked just like a comet. And I was asked, what do you think about that? Here is a comet. Doesn't it argue that Oumuamua must be natural as well? And I said, well, when you go down the beach and you see a plastic bottle and after that you see a rock, that doesn't make the plastic bottle a rock. Next. Next.
Avi, this
Next.
is Stephen. Just to let you know, you're in about a 3-minute warning.
Next. Next. Okay. No. Back. Sorry. Back. Okay. So they say a picture is worth 1,000 words. In my case, a picture is worth 66,000 words, the number of words in my book. I wouldn't need to write the book if I had a picture like this one that was taken by OSIRIS-REx of the asteroid Bennu. And it actually took a sample from the asteroid that it will bring back to Earth in 2023. And so the idea of the Galileo project is to design a mission that would take a close-up photograph of another Oumuamua-like object that we discover on its approach to us. Next. And one thing to keep in mind always is that we are born to this world like actors put on a stage, and we tend to think that the play is about us. But it's not about us. The play has been going on for 13.8 billion years. We just came at the end. And the best way to find out what the play is about is to look for other actors. Maybe they had more time to figure it out. Next. And we can look in many different ways: industrial pollution, city lights on the surface of, on the day side of, on the night side of Proxima b, beams of light that are used to propel light sails, or photovoltaic cells that have a special reflectance on the surface of planets. Next. And of course, there is this paradox posed by Enrico Fermi about 70 years ago. Where is everybody? Well, that to me sounds presumptuous, because it assumes that we are sufficiently interesting and special for them to come over and have a party in our backyard. And suppose, you know, they came 1 million years ago, we will know about it because our documented history is only 10,000 years old. Next. And most of them are potentially dead. Next. But instead of searching for radio signals, as we have been doing in SETI for 70 years, we should search for relics, for equipment. And it's sort of like archaeology, finding evidence for dead civilizations that predated us. Next. And my hope is that this will provide inspiration for the human species, because if you look at human history, the one repeating theme that you find is some humans, some people trying to feel superior relative to other people. And the best example is the Second World War, where the Nazi regime triggered the deaths of 75 million people. That was 3% of the world population in 1940. It's 20 times more than the number of deaths caused by the COVID-19 virus. And we keep talking about COVID-19 all the time. That's 20 times more just by a group of people trying to feel superior relative to other people. And my point is, if we find a smarter kid on the block, a civilization that is far more advanced than we are, just imagine the Perseverance rover, instead of finding evidence for some early life on Mars, instead of finding evidence for microbes, it bumps into the wreckage of a spaceship that represents a technology far more advanced than we ever used. Perhaps that would inspire us to ignore our small genetic differences and cooperate as equal members of the human species. Thank you. I'll be glad to answer any questions.
Avi, I hope you can hear the applause in the room here. We're actually over schedule already, so we're going to limit ourselves just to one question. Dennis?
Great. Our question is, why is Oumuamua always depicted as an elongated rod-like object, while the probability is 90% to be a flat disk?
That's because this depiction was made by an artist. And so what we knew from the light curve is that the variations are by a factor of 10. And it means that the surface area of the object projected on the sky changed by a factor of 10, because if the albedo remains constant. And think about a piece of paper tumbling in the wind. When you look at it sideways, it looks like a cigar, but intrinsically it's flat. So if you analyze the reflection of light from the object, at the 90% confidence, you infer that it's flat. But projected on the sky, it sort of looks like a cigar. And I think the artist was just wrong in plotting it as a cigar. Yes.
Thank you.
Okay, and we've got many other questions, but I'm going to try to keep us on schedule. So Avi, I may be sending you an email string of some questions that people are asking a little later. So anyhow, with that, Phil Mauskopf is approaching the stage. Phil is our first in-person plenary presenter today. Take it away, Phil. Thanks. Not clicker. You need a clicker.
Okay, well, that was a great start to the second day, and also welcome everyone who's here in person to sunny Arizona, given that it rained this morning. I'm Phil Mauskopf. I'm from Arizona as well, but from up the road at Arizona State University. And I'll be talking to you today about something that Avi introduced, the Breakthrough Starshot project, and my role, and I'll be talking about the communications challenge for exploration of nearby stars and star systems with low mass probes. So this is relevant and has been kicked off by this Breakthrough Starshot mission. So Avi gave an introduction in the middle of his talk, which was great. So I can go through this quickly. And then also later today, Pete Warden will be giving another overview of the mission as a whole. But just to remind or to set the stage for the rest of my talk, I'll just summarize that the mission currently is planned to send light sails to the Centauri system, as Avi mentioned, cruising at 20% the speed of light. And the launch system now, I suppose, with some of the other talks that we've had here today, sounds somewhat mundane, but it's using a ground-based laser array beaming light sails and accelerating them. So this is the concept of operations, as you saw in the video earlier, is that there's a launch of the light sails into low Earth orbit or Earth orbit, and then acceleration by the laser, and then cruising to the Centauri star system for 20 years, and then obtaining some images of planets and relaying the data back to us. So what I'll talk about today is some of the challenges in that last part, which is how do we get the data back from such a probe? The main goal of the Starshot mission is to send back from each probe an image or similar type data of the system, and rough numbers are about 100 kilobytes of information. The current technology for sending this type of information is radio communications. That's what has been used for many years in space missions exploring our own solar system. There is now next generation technology, which will be using laser optical communications. So I'll talk about how do we go from where we are today to where we need to be. There are many unsolved problems in this whole mission, including how do we get the power? What is the power source? Various people have been talking about that. How do we do the navigation? How do we acquire the images? But I'll just be focusing on how do we send the image data back once we get it. So one example of current or fairly recent technology, and again, I know I'm aware I'm doing shout outs to a lot of people who are here at this meeting, which is great. So we heard from Alan Stern, who was the PI for the NASA New Horizons mission. So I'm using this as an example of a fairly distant fairly recent communication system, sending the data back from the Pluto flyby and beyond. And so most of the data that we've received from this mission has been sent with a 12-watt X-band transmitter with an onboard 2-meter Cassegrain antenna. The total weight budget for this is tens of kilograms. So the important factors are power and weight for us. And so 10 watts or so and tens of kilograms. And just because they look nice, here's an example of what you can get with that from the outer solar system. You can get images like this this is Pluto's moon, Charon. And this is at a distance from the Earth of approximately 30 AUs or 0.0005 light years. The downlink rate that you have for this type of image is about 1 kilobit per second. And it's downlinked to the NASA Deep Space Network dishes on the ground. And it takes at this rate to downlink all this data, or there were approximately 6 gigabytes of data that were downlinked in the course of a year after the flyby. So for Starshot, what we're looking at is we would like to get images of whatever planets and bodies are in the star system. The speed, of course, that we're traveling is 0.2 C. That's a challenge, obviously, for acquiring images. But the main challenge for downlinking the images, of course, is the great distance. So we're at 4 light years away. The downlink rate that we are targeting is approximately, so it can cover a wide range, but I've put approximately 0.1 to 10 bits per second, depending on the method. And the time to downlink at least one image from a particular probe flyby, again, we would like for that to be on the timescale of similar timescale to New Horizons of about a year. And so the question is, how much harder is this than the current state of the art, and how are we going to get there? So how are we going to achieve this? And so just an overview of the parameters, you can compare weight and power, and then what are some of the other important parameters for such a communication system. And so obviously the two of the big challenges are that we are trying to not only scale in distance, and so the distance makes the transmitter data rate much more difficult, but we're also scaling in weight and in power. So for example, we want to scale from the tens of kilograms of New Horizons down to approximately 1 gram in order to be able to accelerate this on a light sail to that speed. And the transmit power, we're severely limited. So instead of say on order 10 watts, we're looking at less than or so tens of milliwatts of power. And so, but on the other side, we are not quite as ambitious in how much data we need from each probe. So 100 kilobytes versus 6 gigabytes. So if you combine these into figures of merit, you can make a figure of merit, which is the transmit sort of efficiency of your system. This is a figure of merit that is different from, say, the link budget, which is a standard communications figure of merit. This one takes into account the weight and the power. And so I've just calculated this in kilobits per second per distance squared, and then per kilogram or per watt. And this is in order to compare what the goals are for the Starshot communication system with, what is the current state of the art. And as you can see, the current state of the art, if you calculate the figure of merits for weight or for or data rate per watt per distance squared or data rate per kilogram per distance squared, are on the order of tens to 100 in these units. For Starshot, we need to increase this or improve this by about eight or 9 orders of magnitude. So that's the level of the challenge. We have some time, but that's still a lot of orders of magnitude. So one way of doing this is to go to laser communications. That should get you better data rates. An example of this is the NASA's Deep Space Optical Communication System, which will fly on the NASA Psyche mission, which is led by PI Lindy Elkins-Tanton, who's at Arizona State University as well. This system has been developed at JPL and will be the first deep space laser comm system scheduled for launch in the next year. So that's very exciting. So what does this get you? If you use the parameters for the DSOC published in their paper in Nature Astronomy, you get roughly 1 order of magnitude, 1 to 2 orders of magnitude improvement over in these figures of merit. So per weight or per mass or per power over the radio system. However, if you instead calculate from first principles, and so another shout out here is going to Dave Messerschmidt, Phil Lube, and Ian Morrison, who are either in attendance virtually or in person, at least some of them, for some of their papers that they've written on this. You can parameterize the communications data rates in terms of some number of physical parameters of your system. And if you do that and you calculate what is the data rate, I'm going to go through these equations quickly. You actually get that the deep space optical comm system should be much more capable than they are claiming that it will be in the Nature paper by about 2 orders of magnitude. And so if you then include that, you can summarize, okay, how are we going to go from, say, the current state of the art, which is deep space optical communication system, to what is required for Starshot. And so I have in this table that we require approximately 7 orders of magnitude improvement over the deep space optical comms. And I've summarized now 4 different areas where we might gain some of these orders of magnitude. One of them is in what I'm calling the number of bits per photon, or it's really just a calculation of, what is the optimum data rate that you could get for a system with a certain physical parameters. And so I'm saying, well, even if we don't do very much, we might be able to gain, 1 to 3 orders of magnitude, or 1 to 2 orders of magnitude over the published deep space optical communications data rate. Another area is the effective collecting area on the ground. So the Deep Space Optical Communication System is planning on using the Palomar 5-meter diameter telescope as its ground station. So that has, some amount of area, surface area. Obviously, we have a lot of time before we have to actually receive the data. So you could imagine building a really large collecting area on the ground, sort of square kilometers or so. And this will gain you maybe up to 4 or 5 orders of magnitude in terms of your ability to collect photons from the transmitter on board. And then the other ways that we can gain are if we could possibly use the entire diameter, say, of the light sail, or a large fraction of it, then we could increase the effective diameter of the transmit aperture over DSOC by maybe up to 1 order of magnitude. So gaining a few orders of magnitude there. If you add these up, so these are things that we have to investigate and figure out how to do in practice, then it is theoretically possible to get this increase in the transmit order data rate that we require. One of the challenges that's not specifically addressed here is how do we do this and at the same time decrease the mass on board that's required, and that is a very big challenge. So in order to try and move forward and achieve some of these increases, the Breakthrough Starshot project has issued and has started an R&D effort to investigate ways of moving from the current state of the art into the requirements for the Breakthrough Starshot project for communications. This is called the Phase 1 R&D. There are 3 goals. They're listed here. The goals are to develop and refine theoretical concepts, system designs for doing this, design and develop subsystem components for the onboard transmit system, and design and develop subsystem components for a ground receiving station. And this was issued, this call for proposals was issued at the end of and beginning of this year, end of last year. And we received proposals, and now we have selected these groups. They're Phase 1 groups. They're from all over the world, including a group here at the University of Arizona. And work is just starting. So we have a number of groups. These are the summary of the groups and their topics. And so we had the status of this effort is that we had a pre-Phase 1 workshop in April 2020. This was hosted by the Interplanetary Initiative at ASU, which is led by Lindy Elkins-Tanton, who's PI of Psyche. And this was on Zoom. We had over 80 people attending from all over the world. And there's a report from the workshop with slides, models, and these are all available at this webpage at www.starshotasu.com. And then, as I said, we've selected the teams that are going to do Phase 1 research. There was a Phase 1 kickoff meeting just a few weeks ago, September 11th. And so work is now starting. Teams are starting to ramp up. This work and these efforts have potential synergies with lots of things: NASA research, commercial space, security, other communication systems. And so we're very excited about the opportunities and the possibilities. And so hopefully there should be lots of results coming out soon. So that's all. So I'll end there. Thank you very much.
That's great. We've got time for a few questions. I want to remind the people in the room, we're collecting questions on these little squares of paper. So either bring them over here to Dennis or over to Doug at the far end. If you need more paper, we've got more. If you're on the Zoom channel, make sure you get the question where Dennis can see it. And I think you've got one to start with, right?
Yes, we got one. So rather than using them for radio astronomy, could a large antenna on the far side of the moon improve deep space communication capability? And is anyone proposing this?
Yes, so we are not currently studying that in the phase one Starshot effort at the moment. I would say that the potential advantages of doing this on the moon could be that, yeah, if you're communicating at radio frequencies where there's a lot of interference on the Earth, then that would certainly be a big advantage. If you're communicating in the optical, though, if we're doing laser communication, there are some advantages. It's, you don't have any atmosphere, so there's no loss of optical photons through the atmosphere. However, the disadvantages are clearly that constructing, a square kilometer array of optical receivers on the moon is probably a little bit more expensive than doing that on the ground.
Thank you. How can a light sail be used as a laser emitter?
Right, so I think there's two main ways that people are starting to study this. One is by the fact that the light sail is designed to be reflective, because it needs to reflect the beam on launch. And so if you can use some sort of technology to control the surface when it's after it's passed through the star system, then you can use it as a reflector to reflect and focus a beam back towards the Earth. The other thing that's being studied is incorporating into the light sail arrays, say, of a phased array of laser emitters, so that you can use the light sail itself and have little lasers interspersed in the actual material of the sail, and then coherently combine them in order to direct that energy towards the Earth, almost like a miniature beamer on the light sail itself, but obviously with strong constraints on mass and power.
Thank you. Could you improve the order of magnitude capability by using more exotic means of communication like quantum communication or things like this?
So there are several groups actually studying how to improve say the number of modes, or to use quantum information in order to improve the communication efficiency. This includes studying things like squeezing and also entangling, if that is a possibility. There are ways of doing this, but so far it appears that sort of gains are modest. In other words, not orders of magnitude, but maybe one order of magnitude.
Thank you. And finally, are you considering multiple modulation methods to increase bits per photon? For example, polarization, frequency, et cetera?
Yes. So again, there are groups studying those topics. There's polarization. There's a couple of groups that are interested in orbital angular momentum in terms of increasing number of modes. But yeah, and then there are groups just studying the different modulation schemes in order to maximize the information. Anyway, so I thank you all. This was great, and I'm amazed that I was not called for time in the middle of my talk. So I'm glad
you're good. You're good. Thanks very much. And in an odd episode of the collision of my day job with my hobby, Philip, I noticed that Carl Berggren is on your communications team out of MIT. He's part of the Center of Quantum Networks, which is my day job. And I would say we would be thrilled with a one order of magnitude increase in telecommunication sensitivity. So we're working on the one order, the other six are up to you. With that, we're going to switch back to another Zoom presenter, Dr. Gabriel Rizzo. I'm not sure Rizzo or Rizzo, I apologize. Would have been here, but he's in Italy. And as we've already discovered, traveling in the age of COVID is somewhat complex. So he's going to join us by Zoom. I saw him on the call earlier. Dr. Rizzo, if you can say something, I'll know you're online.
Yes, I'm online.
There we go. It's all yours. Take it away.
Well, thank you. I can't see myself in the video. I don't know whether there's an issue or not. But anyway, I'll just keep going by wishing good morning, everyone. And right in the middle of the matter here. So recently, I was in my LinkedIn feed, and one of my connections sent me a commentary on an article that was talking about warp speed and physics. And I was like, yeah, but that's from Alcubierre's metric in 94, and that's got negative energy in it. So we're still quite far from it. But then I actually read the commentary. And that was from the National Institute for Astrophysics. And that wowed me because the negative energy constraint was gone. Next, please. In the next 20 minutes or so, I'll cover some of the literature about warp drive and how it shed a light on possible ways around the fundamental constraint of c, the speed of light. We will unpack the issues that we encounter along this journey towards warp, and then I will offer you an outline of the positive energy construction by Lentz. As this has the potential to move FTL travel to an engineering problem, it's also worth understanding that there's so much that we can see from the bridge of a notional USS Enterprise moving at warp speed. Spoiler alert, it's not what you see on TV. Next. So what is warp? It's a curvature and stress energy solidon, namely a self-reinforcing perturbation in spacetime that maintains its shape while it propagates. We're not covering general ways to travel faster than light, only ways of moving faster than light. So I am sorry for all the wormholes fan out there, and I'm a wormhole amateur myself, but no wormholes here. As it's impossible to propel matter to speed greater than c, we need to create something different. The idea is to generate a perturbation, the solidon or warp bubble, that is able to enclose a region of spacetime where a payload, the starship, is able to sit and be transported across spacetime. That is what is shown in the figure at the bottom right, the top hat function. That is the spacetime expansion factor, following White and Davis, of a warp bubble, specifically Alcubierre's here. And we'll see this in a moment. You see there is a steep wall that is the actual warp wall, the warp region, and then a plateau that is the inner region of the bubble. This highlights a general property of warp drive spacetimes that is actually a very desirable property, namely that proper time of the spaceship is equal to coordinate time, for instance, time on Earth. To study warp drive spacetimes, we'll find very useful thinking, looking at energy, and thus using the Hamiltonian formulation of Arnovit, Desen, and Misner. We do this through the 3+1 or ADM formalism. That's the ds squared you see in the top row, where we foliate spacetime in equal time 3 surfaces. And then we study the relocation through the shift vector Ni. Of course, the ansatz is that 3 surfaces are flat. So the Hij there are chronicle deltas. Next, please. Alcubierre proposed in 1994 a metric motivated by cosmological inflation that would allow arbitrarily short travel times between 2 distant points in space. Alcubierre metrics is what you see in the top row there, and it corresponds to setting a nx equals to ny equals 0 in the ADM decomposition we introduced just before. The enormous speed of separation arises from the expansion of space-time itself, analogously to the inflationary phase of the early universe. More specifically, the hyperfast travel is induced by creating a local distortion of space-time, as shown in the figure, where you see that the local volume expansion. Alcubierre's warp drive model produces a contraction ahead of the bubble and then an opposite expansion behind it. What is extremely interesting here is that it can be shown that the observers with 4 velocity 100 v times f, that's the ones that are in the spaceship, move along geodesics as their 4 acceleration is 0. And these observers are usually called Eulerian observers in the 3+1 formalism, as they move along normal direction to the spatial slices, you remember. The spaceship, thus, can be easily seen to move always along a time-like curve And we can also verify that the proper time along this curve equals the coordinate time. Next. It was thought this distortion was the reason warp drive space-time worked. Space in front of a given region is contracted, whereas space behind the same region is expanded. In response, the warp bubble moves forward with a speed determined by contraction-expansion rate. Natario, however, showed in 2002 that this contraction-expansion is not necessary at all, and that in particular, it is possible to construct a similar space-time where no contraction-expansion occurs. Heuristically, one could best describe the warp drive spacetime as sliding the warp bubble region through space. Space in front of the warp bubble may get contracted and space behind it expanded or not, depending on the details of the construction. Natario's construction is more geometric rather than differential, and it is not as straightforward as Alcubierre's to be read. But luckily, that algebra was unpacked recently by a group in Texas, Mattingly et al., who I would say rightly wanted to brute force Natario's warp drive metric into some visualization. As they say, while the mathematics of a warp drive is well developed, the mapping of space-time around warp drive remains hardly explored. Considering that a ship inside a warp bubble is causally disconnected from the exterior, computer simulations of the surrounding space-time are critical for the ship to map its journey. And you can see in the pictures here, the curvature invariant, some curvature invariant, this, namely the richest color for Natario's warp drive. We have to get it short here. Next. There's no free lunch though. I've taken all the bad news last for you. The first is that as we cross the threshold of the speed of light, horizons form, in the sense that events inside the warp bubble cannot causally influence events on the other side of the surface. There exists a similar horizon in front of the starship, a conical region, inside of which no signal can be received from the starship, but where points are visible from inside the warp bubble. This is called the visibility horizon. These horizon-like structures are the four-dimensional generalization of behavior originally discovered in examining two-dimensional warp drive spacetimes. These two-dimensional warp drive spacetimes contain event horizons surrounding the starship whenever it moves at speeds greater than c. The figure on the left illustrates how the half angle of these horizon-like structures grows steeply as warp speed increases. These structures are somewhat analogous to the familiar Mach cones associated with supersonic fluid flow. Next. Next, please. When we switch on quantum effects, the situation does not improve. Hiscock in 1997 first discovered in two-dimensional space-time that the backward and forward walls along the direction of motion look respectively as the future and past event horizon of a black hole for an observer inside the warp drive bubble. This means the starship's crew see a black horizon aft and a white horizon fore. It is very important, however, that the horizon first appears at infinity and moves inward as the speed is increased. Unfortunately, it comes very close very fast, as the singularity is located at a R star such that f of R star equals 1 minus 1 over v, with f being the top hat function that we saw at the very beginning. Remember, the top hat function is 1 inside the bubble and 0 outside and grows steeply inside the bubble's wall. This means the horizon is at infinity when v equals 1, meaning at the speed of light, because it's 1 minus 1 over v. So with v equals 1 is 1 minus 1, and thus 0. But as soon as v grows greater than 1, the horizon appears in a counter image of that value inside the warp bubble, inside the warp walls, up to arriving at its inner boundary for v equals infinity. The central region of a warp drive behaves like the asymptotic region of a black hole. In both of these regions, the static energy density, the one that is dashed, the solid line in the figures, vanishes. You see from the lower row, and the whole energy density is due to the Hawking radiation generated at the black horizon in the back wall. The formation of a white horizon produces a transient radiation, which accumulates on the white horizon itself. This causes the energy density, the total energy density, to grow unboundedly with time on this horizon. And thus, the semi-classical back reaction on the renormalized stress energy tensor will make this superluminal warp drive to become unstable in a time scale of the order of the inverse of surface gravity on the white horizon. That's roughly the inverse of the temperature. There's also a Cauchy horizon, that's wrong in the slides. It's a Cauchy horizon producing infinite blue shift of the black horizon Hawking radiation. Next. And last and the best, negative energies. We start with energy density, bottom left, 8 pi E equals 1/2 of that, where we have already projected the Einstein equation onto the hypersurface normal. We're working still in the idea that we're slicing space in equal time slices. The geometric side of the energy constraint equation is divisible into the intrinsic hypersurface curvature, that's R3, the extrinsic curvature trace, Kii, and its quadratic hypersurface scalar, Kij, Kji. As we want the Hij metric of these foliations to be the Kronecker deltas, so be flat, the intrinsic curvature R is 0. All the three Alcubierre, Nattario, and Lenz constructions can be classified through the characterization by a shift vector potential function, namely a function phi with spatial gradient related to the components of the shift vector. So each component of the shift vector n is the derivative of phi. Imposing a relation between all the shift vector components makes the trick. The most common relations explored in literature are linear and elliptic. Specifically, the linear relation is Alcubierre's warp drive spacetime. That's nx equal ny equals 0. And you get the result in the bottom center. And that is actually a toroid of negative energy perpendicular to the direction of motion. That's the figure on the top. You can imagine that the motion is happening from left to right. So it's towards your right. The spaceship is flowing towards your right. So you see that in Alcubierre's warp drive, the sources of the shift, that's these negative energy toroid, are completely out of phase with respect to the expansion contraction factors that were forward and backward. The zero expansion feature of Nattario's construction is captured by the elliptic relation divergence of n equals 0 and restricts the energy form still to a negative quantity. Francisco Lobo in 2017, and again Alcubierre in 2021 tell us that we need energy m warp of the order of minus v squared r squared times sigma. That's basically the inverse of wall thickness. So you see that there's a component of the wall thickness in the quantity of negative energy that we have. To recover the
Dr. Rizzo, Stephen, just letting you know, we're on about a 3-minute warning. If you could kind of get to your last slide, we've got a lot of questions coming in. Thanks.
All right. Okay, so next one. So we can have a positive energy construction if we look at the construction of the energy constraint. You see that there's a possibility to have an island of positive energy configuration by arranging a suitable potential. Next. And that's the soliton. And the lens soliton has a lot of considerable and remarkable properties. This is a soliton for traveling at warp 2 from Star Trek, namely 10 times the speed of light. The configuration is such that the wave fronts you see in the bottom center, that's the density of this hyperbolic sources. They're arranged in this diamond shape configuration. You see that the energy is practically overlapping to where the sources are. You see that the shift, so the tidal forces allow for a high and level center zone that's practically tidal force free, and in the top center figure in the left one, that's the shift towards the front, that's the Z shift. Blue is in forward and red is backward. You see that there's still there's a wide area where we have strong push in the front. This construction still has time that is equal to coordinate time, so still very remarkable. And the energy quantity can be shown that an energy for a bubble of air of R 100 meters and wall thickness of 1 meter is 0.1 solar masses. And this brings a lot of other consequences to the constraints that we saw before, for which we don't have time to discuss. So very open to questions.
Thank you, Gabriel. We have quite a few questions, and so these are good ones. But let's start with: could a warp bubble propagate at superluminal velocities, or might there be a maximum propagation rate, perhaps at C?
No, the warp bubble is space-time itself. There's no propagation. There's a regional space-time that is moving across space-time. It's like with inflation. You don't have a upper speed boundary when it comes to inflation. It's space-time itself that is moving. You don't have propagation inside space-time. So there's no upper boundary to the speed that we can achieve with this construction, relatively to fundamental constraints like C. There's other problems with horizons, with semi-classical instability, with mass energy components, and a lot of other stuff, but we're not in principle bounded by speed.
Thank you. Would space being discrete pose a challenge to creating a warp drive?
No, I would say no, because there's a couple of answers here. This is not a construction that relies on a quantum structure of space-time, so it's a classical construction. Having a high energy cutoff like strings or loop quantum gravity may improve issues with negative energies. I think there's a paper of 2002 where there's a good discussion on on how the energy conditions are basically moribund, and how this needs transition to a new and now widely accepted idea of quantum inequalities. But I would say no, I don't think so.
Okay, great. And finally, could the trajectory of a warp bubble be affected from within the warp bubble?
No, it can't, because you're causally disconnected. The inside of a warp bubble is causally disconnected to the outside of a warp bubble. So the only thing it can be driven as long as so there's no way you can decide where to steer depending on the information that gets to you. But you can modify at a certain time the charges and the sources of this deformation so that you can actually steer or change the trajectory. That you can do, but you have horizons in the back and in front of you. So you cannot react to anything that comes to you. And that made me think of when in Star Wars, actually, there's the whole idea of hyperspace. But when they're doing the computations to do the hyperspace jump, and all these computations remind me of we need to waypoint our trajectory because we cannot control our trajectory reactively. We can only plan for it in a warp bubble.
Thank you.
Dr. Rizzo, thank you very much. I appreciate that. I can see by the number of questions being passed in, if you were here in real life, you would find it very hard to get from the podium to the coffee because I think you would be swarmed. But thank you again. It is time for coffee. We're a couple minutes behind schedule, but we'll get back on schedule. The two most important portions of the morning here are now coffee and communication. So everyone gets a chance to do both of those, have a chance to network, ask each other questions, chat a little bit. Coffee is set up on the Canyon Room down the hall. Be back here at 11 o'clock sharp. Thanks very much. All right. I hate to cut off all these conversations because they're fun, but we're going to try to open up the next session. I neglected to mention, I don't know if Dr. Loeb is still on the Zoom or not, but I neglected to mention one of the discussions he had about observing technosignatures on Proxima Centauri B. An undergrad student co-authored a paper with him on that, and she has a poster in the Ventana room. So if you haven't looked at Elisa Tabor's poster, you probably would enjoy that. And I promised I was going to mention that. We're going to get back started with a live presenter who came from all the way across campus. One of my colleagues here at the University of Arizona, and a friend, and somebody that I'm thrilled is on our faculty, and who works on some of the coolest projects that I ever get a chance to play with. Is Dr. Jehan Thanga, and he's going to talk about cryopreservation. So Jehan, over to you.
Thank you for this, and what a great conference, particularly. Oh, this way. Yeah. Okay, great conference, and I just wanted to say, I'm just learning really a breadth of whole new knowledge areas in this really interesting space. I just wanted to acknowledge my co-authors here, Alvaro, who's in the audience, in addition to our Claire Pedersen, Athip, and a few others, of course, who have been working with us on this. So our topic here is cryopreservation of organisms in space in preparation for interstellar travel. And I just want to quickly go through, and this has been echoed right throughout this conference, is what is our real motivation to want to leave Earth? And of course, we have a whole bunch of potentially extinction scale events that have almost gotten us or will in some time in the future. In fact, we've had very close calls. Added to that, now we have the additional powers of being able to destroy ourselves, probably in a very limited time frame. And so, putting all of these factors in here, really from a preservation point of view, we are under serious threats. And really one of our closest calls that we had was about 75,000 years ago. That was thanks to a supervolcanic eruption. But throughout our history, we've had major cataclysms. In fact, the end of empires, such as the Minoan civilization, due to the volcanic explosions in the Greek peninsula. The other has been the Great Fog of Middle Ages. The term Dark Ages comes from that, and of course, the bubonic plague that wiped out much of Europe, and more recently even the smallpox epidemics that wiped out considerable numbers of people. So cataclysms are really the norm, and really one of the most dangerous ones, where humanity almost got wiped out. At least that's what the data seems to suggest, was the Toba supervolcanic eruption that happened about 75,000 years ago. It would have impacted much of the southern hemisphere. At about that time, much of humanity would have been in Africa, but also sort of spreading out into Asia and much of the southern hemisphere. And this resulted in a cooling period, supposedly for about 1,000 years. There's been traces of ash all throughout the southern hemisphere from this impact event. And that aligns well with a considerable drop in human diversity. So, our current theory suggests we're at least about 200,000 years old, Homo sapiens sapien. But if you were to look at the genetics, we can only go back to about 75,000 years, which is this event. And so that suggests that there was a really narrow culling of humanity, perhaps down to a few thousand folks. So given all of these factors, given the advancements that we're seeing and very exciting advancements, particularly being able to see exoplanets and being able to even notice habitable zones, surely, one of our future goals would be to, hunt for a Earth 2.0. What I wanted to say there is, we have to also sort of balance ethical and moral grounds here, particularly if we're, going after this new planet to habitat, it probably is not already habited. And so it is perhaps, going to become habited, but not currently there. And so that would make a case for why, we could go on this interstellar trip. But nevertheless, there are going to be huge challenges, as I'm going to just talk about, not just, the propulsion element or the physics element, but really the human factors element and really being able to put this mission together. And in that sense, and I'm going to focus more on the human factors element and the mission is to do this. Not only should we have to travel with a human crew, we'll need to bring quite a lot with us. Perhaps Earth's diversity with us, and that's really needed just to keep ourselves healthy, to maintain our quality of life and so on. But there's also challenges here. If this thing is going to take many generations, will future generations still have the zeal to continue with this mission? Along the way, is there going to be conflict between the human crew? If it's too rigid rules, it may lead to disobedience and civil strife. If it's too lax rules, it may be leading to even splintering and separation. So it's unclear really how future generations would react in a multi-generation mission like this. And added to this, of course, the physics effects of relativity and so on. So the challenges here, of course, is that this interstellar ship, where we're sending perhaps humanity's future, is going to be vulnerable. Its resources, relatively speaking, are going to be scarce. And what we have learned with putting humans in congested environments for long periods of time so far hasn't shown the success that we really desire. And so, the question is, can it lead to chaos and unexpected outcomes? Given these factors, and given the need that we need to carry, biodiversity with us, particularly medicines, rich source of food, need for our well-being and health, it's really quite hard to separate the human side of these things from the ecology side, and we need to really be able to carry both. And so, how much of Earth's biodiversity can we take with us, and if we're really serious about, colonizing? So one of the things I think that does give us hope looking at this area is the ability to put creatures into cryogenic sleep. And this can significantly slow down their aging process. By putting them into sleep, we can also avoid having to bring along resources and having to consume these resources. So no need for vast food reserves, entertainment, maybe even regular living quarters, because we're going to be able to put creatures to sleep. And ultimately, or ideally, you would have your crew and passengers wake up near the destination, ready and fresh to go. And what about in between? What about till that last leg of the journey? Perhaps the use of robotics to really take care of everything else. And so with this, that's sort of the aspiration. But that's what we have been trying to see from this research, how far we can go with such an aspiration. Particularly, it could be enabling for interstellar travel, of course. The other is to protect Earth's biodiversity in a safe spot, well away from the cataclysms of Earth. But it can also be transformational towards life here, from a medical point of view, increased quality of life, and really be transformational there. So there are some great success stories I wanted to just mention to you guys. That is, we have, for example, seen one species of plants come back from extinction. This is the Judean date palm. At one time, it was widely valued in the Israeli and Palestinian areas, and due to human history, it went extinct. And however, some people in those historical times had the courage to save these seeds, and this was near the Black Sea, and they were well preserved, and they were actually able to bring this back to life in the last 10 years or so. And so this was something that's 2,000 years old that was brought back to life. Pushing even further, we've seen Arctic flowering plants that have been preserved for 32,000 years brought back to life. And another example, perhaps more related to the subject here, is we've had cryo-frozen mice, and this was a Japanese-led research in which they had it frozen on the ISS for 6 years, then brought it back down to ground, had them, live off their lives, and you literally had, pups of mice come out from this, and seemed to be healthy and unaffected. So these show some of the great potential, but there's still, long ways to go. The other is I wanted to insert that, given these advances, really our highest priority would be to try to protect diversity. And there's already efforts going on with this, particularly through the Southbod Seed Vault. But, could we scale this up towards protecting all of Earth's diversity? And so that could be a, modern day global insurance policy. And one of the things that we have proposed is setting this up on some of the lava tubes on the moon. It's only about a 4 to 5 days journey from Earth. And these lava tubes are likely pristine or have been pristine for about the last 3.5 to 4 billion years. There's nothing like this on the surface of Earth. Everything else gets recycled on Earth due to plate tectonics and whatever else. And so, this could be the place to go for preservation. But let me just jump into cryopreservation here, and that would be the the route to do this. To date, there has been success of cryopreserving eggs, sperm, stem cells, individual cells. But going beyond that towards multiple organisms is a whole different story. And to date, what they've noticed is you can actually control the degradation, and the technology is definitely maturing, and it works. It is possible. The challenge, though, is also another sort of leg of this. It's called cryonics, in which the attempt is to preserve an entire body. And here people have been trying to use that as a means to try to extend their lives beyond death. So you take someone just about to die, put them into this sort of cryopreservation cryonics lab. And the idea here is to wait for a time in the future when they're back in again to be brought back to life. Or maybe we can overcome diseases that they're being inflicted with and such. The biggest challenge here is the freezing. The freezing causes ice crystals to form, and it can damage the body internals irreversibly. Now, newer techniques use cryoprotectants for this, which are sort of antifreeze type substances. Natural creatures live in the Arctic, and they can live in a surrounding where everything is frozen, but they actually have a natural antifreeze that actually protects them, but not to cryogenic temperatures, of course. So the general agreement is this technology is pretty much daunting, unlikely to see a breakthrough in our lifetime in this case. However, what I think is a more practical alternative is this idea of torpor. And that is going into a hibernation stage, much like how bears hibernate, or much like how our other mammalian cousins hibernate, but really adapting that to humans. And so this is a technology that's been advanced by SpaceWorks out of Atlanta, Georgia. And they propose putting humans into this hibernation stage. And we have encountered torpor type situations in the emergency room. Particularly, there have been these, random instances when, for example, people have fallen into a frozen lake bed, and by all standards, they should be dead, but instead they come back alive. And they're close to death for many hours, maybe even days, weeks, but they come back to life. And this is thanks to this phenomena, where and through torpor particularly with what SpaceWorks has been able to do, is to actually sort of environmentally control the situation and really bring it into an application mode as opposed to a sort of a reaction mode here, and bring down the temperature of the body down to down below, your regular 37, down by 10 degrees centigrade. And at that point, your body slows down, becomes very low metabolism, and you can use this. In fact, they've been using this to save patients from some of the crisis modes these days. So with torpor, your body is slowed down, it's not stopped, so it still needs resources, it still needs food, it still needs air to sustain itself. And of course, the body is going to age, but at a very low metabolism. And so overall, it's reduced complexity. Lower metabolism means lower resources needed, big savings in mass and volume possible if you're going to put them on a spacecraft, and viable for years. But of course, it's unclear, the effects of radiation here. And of course, it's unclear what the upper limit is. Is the age still going to be about 100 regular humans, or is somebody torpor extended, for 50 to 75 years? Are they going to have double their lifetime, perhaps? We don't know that yet. So one of the things we wanted to sort of investigate is can we start, recreating some of these situations with cell and fundamental experiments? And so to start there, particularly to understand, for example, lunar conditions, we can try to recreate that using a centrifuge. And we've been looking at ongoing efforts there with AOSAT and AOSAT Plus, which are centrifuges to try to recreate asteroid environments. But using the same principle, we can push that towards recreating lunar environments on an on-orbit lab. And so our proposal here is to set up an on-orbit lab that would maintain conditions at cryo and be able to take with us, and let me just quickly jump through 3 different organisms: tardigrades, mice, chickens. And we figure these would be some of the earliest to try, and you would put them in this centrifuge, which would operate at cryo temperatures and be spinning and producing lunar gravity. And so far, we have done some early concurrent design studies. We look and see it's pretty feasible for a few $1 million. It'll require about 0.5 kilowatt of power, but that's something that we can definitely utilize on the International Space Station. And so with that, really, we're at early stages here. There are potential wide-scale benefits from this whole way of looking at things, of being able to preserve life for long periods. And of course, the big application and most relevant here is interstellar travel. There are human factors involved that we can't completely ignore. But really, the options that come up, if it were to be directly applied to interstellar travel right now, is to be able to send eggs, sperms, seeds, and so on this trip, and have them grow on that trip at the last stages. And so that is a possibility with the current paradigm, but we're going to have robots really run the whole system until then. So that might be a huge leap. That might be too risky for us in our current paradigms. However, if we're desperate, if we're not in a situation that we're in the present moment, maybe that becomes viable, right? So having said that, the other, of course, is torpor, and it's very definitely viable, but that can only last us for decades. And so if it's a shorter term mission that's going to be a few decades long, then I think torpor is it. So with that, thank you, and I'd be happy to take your questions.
So within torpor, how do you overcome biological degradation like muscular dystrophy in the cryogenic sleep?
So with the body going into that state, none of these other factors seem to develop. So that's interesting. But this is only based on some of the limited studies done. But even with torpor, it has not been done at the scale of years. So it's only been done for days and weeks. So that tells you there's still lots to study.
Can you talk a little bit about the biological antifreezes at all, and like the mechanisms about how they disrupt the ice crystal formation?
Sure. So there have been sea creatures in the Arctic ice that live, and the surrounding temperatures could, if it was water, it would lead to instantaneous freezing. So these creatures have adapted to have literally antifreeze type liquids circulate their body and keep them from freezing. And it's native to those creatures. It'll be, of course, interesting considering how much we have been advancing with genetics, of how much we could borrow that and perhaps use that to augment the human body or mammals in general. And that could be an interesting pathway, but nothing really has been done in terms of the augmentation yet.
Mhm. Are those glycol-like molecules?
Well, they have, the lower freezing properties. I'm not specifically sure, if they're glycol related, but I would imagine, they're producible, with sort of this whole ecosystem of biochemicals, as opposed to your regular antifreeze, which is quite poisonous and toxic.
Yeah. All right. Thank you very much.
Thank you.
John, thank you. Appreciate it. All right, we're going to switch back to one of our Zoom presenters, Dr. Fatima Ebrahimi. I was really looking forward to having her in Tucson, coming from Princeton, another one who got caught by COVID and travel restrictions and so forth. But Dr. Ebrahimi, if you can say something, I'll know you're online.
Yes, I'm here.
Great.
Can you see me?
You've got the floor. Thanks very much. Appreciate it.
Thank you. Really, thank you, Stephen, and thank you for inviting me to talk about this technology. And I wish I was there and meeting you all. And so I'm plasma physicist. So it's a little bit, we are switching a little bit different. Plasma physicist from Princeton Plasma Physics Laboratory and Princeton University. And I will be talking about an original concept that I invented in 2017 about reconnecting plasmoid propulsion. And just a little bit clear if there is any confusion, that I'm not affiliated with the group that yesterday nicely presented. Hello? Yeah. And next, please. Yeah, thank you. So, so for any kind of deep space propulsion, we know that the space and fuel efficiency is really critical. And for this kind of high delta V, any kind of mission, you really need high thrust electromagnetic propulsion with high exhaust velocity of tens to hundreds of kilometers per second. So the question is that how would you, realistically, how can we actually achieve that? How can we break the boundaries? And as we heard so many nice talks, how can we get to those kind of speeds that that we can actually go for much deeper space propulsion system? And next, please. I think you need to, yeah. Interesting. So the movie showed. It didn't show on my computer. So for that kind of a speeds, actually, we don't need to go too far. And we can look at our sun, which is actually producing a lot of magnetic energy under the surface of sun. Because of the relative motions of the plasma motion, you will get a lot of magnetic energy buildup, which is not only magnetic energy. Interestingly, it's a lot of twisted magnetic field lines, linked magnetic field lines that are being generated in some zone of the sun called convective zone. And sun cannot handle that. You have so much buildup of magnetic energy and wants to get rid of it. So, and this twisted linkage of the field lines, we call it magnetic helicity, coming from helical. So this magnetic helicity wants to get rid of that buildup of what is making constantly. So how does it do that? That's by actually flares, you know, it kind of finds a way to inject these kind of magnetic helicity into the surface of the sun. And then to do the flares, the process we call magnetic reconnection, when these field lines come together, and then the whole magnetic energy is being converted to kinetic, mostly kinetic energy and other forms. And sun releases a lot of, you know, plasma and particles with a velocity of hundreds and thousands of kilometers per second. So this concept that I will talk today is exactly that. It's a controlled version of that, which is the combination of the injection of the magnetic helicity and the process of magnetic reconnection, when we directly actually magnetic energy is being converted to kinetic energy. So it's a form of propulsion that for the first time you actually get kinetic energy that is being generated directly from magnetic energy. And next, please. So and then, so this reconnecting plasma drive, the concept that I will be talking today. So of course it's been, because I'm also a fusion plasma physicist, it's come from or inspired by fusion, but also it could work with different power sources, solar powered and nuclear electric fission powered, and also nuclear fusion. So it could work with that. And then it depends, the thrust that is going to produce, it depends on the power that actually is provided to this propulsion system. Next. So there are two physical mechanisms that needs to join for this propulsion system to happen. And one is, as I said, is the magnetic reconnection, which in the middle you will see that the oppositely directed field lines, magnetic field lines, when the magnetic field is get annihilated, so it kind of gets reconnected, and you will get, you know, kinetic energy. But what we discovered a few years ago, including myself, that there is some kind of a plasma regime that actually you can jump from these kind of a reconnection regime that was really slow to kind of fast reconnection regime. And that was the regime, we call it reconnecting plasmoid regime, that these field lines, when they come together, the faster you kind of these field lines, they come together, they break, and then they make more and more round objects, magnetic objects that we call it plasmoids. And then they can be bigger and bigger plasmoids can form, and they can actually, the plasmoids can carry a lot of momentum. Which is usually, we call it alpha in velocity, carry a lot of momentum and kind of exit in terms of the kind of exhaust velocity from the location reconnection site X point. And so that's the basic of it, that how we can actually find, it's kind of a new fundamental physics that we discovered in plasma physics, that we are if we are in this regime of parameter, we can actually get really, really high, fast magnetic reconnection in these plasmas. And next, please. And probably skip that next. So how do we actually make this kind of reconnection sites that we get this plasmoid reconnection? And that's true, that's the whole point of this concept that I'm going to talk, that I'm talking is the helicity injection concept. And that means that, like what I showed in the sun, you actually need to inject a lot of magnetic helicity, and there are places in the plasma that actually you have this reconnection site, fast reconnection site, that you can get the momentum. And the injection of the magnetic helicity is not something new. I mean, we knew about it since 1959 by Alphen. In his experiments, it actually created this kind of a solar type magnetic rings with his team in his experiment. And since then amazingly in the experiment in different configuration, toroidal, spherical, linear, for different reasons in fusion plasmas, we have been doing injection of the helicity in our devices for mostly for confining the plasma or actually generating current for fusion. But so far, no one has actually had been proposing a practical application of these helicity injection for space propulsion. And that's what this system is, that with the magnetic reconnection, you can combine that with helicity, and that's how you can get the kind of real high trust and high ISP with this technique. And next, please. And to the left is the schematic of this propulsion system or a connecting plasmoid drive that by carefully configuring these magnetic coil, like the sun or like the Alfvén experiment, you can actually inject a lot of flux. And what you need to do by this configuring in this coil, you actually provide some reconnection site that the flux that you have been injecting, it can actually, you get rid of it, like what the sun does, you get rid of it by the process of fast magnetic reconnection. And the flux then interestingly become like an elongated form of the structure or round, we call it plasmod or, compact, and leave it. And since it's the whole plasma leaving the device, it produces a lot of thrust and also it produces a lot of high ISP. And with the exhaust velocity is about, 20 to 500 kilometers per second. And the nice thing is that also this is a plasma, and it has been shown in this paper that you can actually run this propulsion system with gases, including hydrogen, even light gases. Next, please. And then, so how do we actually know that this works? And that's been by doing really realistic simulations. And so the simulation has been done in a thruster configuration in the largest or biggest supercomputing at NERSC. And all of the simulation that I show, it's based on the schematic that I showed in the previous slide. So with realistic simulation, please next. So we find a very high exhaust velocity through the process of fast magnetic reconnection. And there are two plots here are shown that shows that how important the fast magnetic reconnection is for producing high ISP in this system. So to the left is just the conventional plasma accelerator like plasma guns, etc., that you will get some velocity. But to the right is when you actually combine it with fast magnetic reconnection and you get an order of magnitudes higher specific impulse. So you actually can achieve very high exhaust velocity. So it's only not injecting magnetic flux is not the only way. You actually need to have both for this to happen. Next, please. And then here is also, again, more and more, detail, really in detail, we have explored this concept that does it depend on the model that we are actually simulating. If it's fluid type models, MHD, or more kinetic type models, if we include more kinetic behavior of this plasma, is it robust or not? And that's exactly is that it's robust. You can actually get this formation of these plasmoids with high velocity. So the physics is actually really the same for these different types of physics model that being incorporated in the simulation. And again, the trick here is that it's all based on the fundamental plasma physics that we discovered in the last few years. You have to pass this threshold to be in a plasma parameter regime to get to this fast reconnection regime to get this high exhaust velocity. Next, please. And again, the cyclic behavior of this formation of these plasmoids are important. Usually some of these propulsion systems, they have this detachment problem, but here actually nature and the field lines, because of the process of magnetic connection, it detaches itself. So the detachment is not a problem. And you get this cyclic behavior, cyclic formation of this form of these plasmoids with a periodicity. And that's as long as you have this static electric field available. And of course, you can actually program your voltage and make it pulse. That's also an option. That's I have studied in a few years before. Next. And then again, this shows what we started with our son, yes, and that it's from realistic simulation that you see these twisted field lines that generated in the in this 3D simulation, momentum carrying structure plasmoids that are formed. So you need a specific coil configuration that produces this momentum carrying structure and leave the device, leave the plates at X points with a high velocity, these plasmoids. And it's all twisted. So you actually, sun makes his own magnetic field. We provide it and convert it to kinetic energy through this process of magnetic reconnection. And next, please. And it's definitely, this is really highly scalable. And this is not something that is projected. All of these points that it's seeing, the ISP is really numerical points from realistic simulation that you see that you can achieve highest speed, and as long as you provide more and more magnetic field. So it scales nicely with magnetic field. And also the thrust calculation, which has been done in this paper, also shows that it scales nicely with magnetic field. So the scalability of the higher specific impulse and also the thrust is really important, and it scales nicely. And next, please.
Just so you're aware of time, you're about 3 minutes, and I see a lot of questions coming in, just so you're aware.
Okay, thank you. And then the next thing is the whole thing is inspired again in an experiment that I was working, a fusion experiment. So, and we made this blobs or plasmoids through plasmoid reconnection. So this camera images to the right shows that we have the proof of principle, and routinely we made that for creating a startup current in these experiments, and the simulation predicted that. And there is a image, but that's supposed to be in the paper a few years ago, the movie of how actually these structures lives and produce with high velocity of 20 to 30 kilometers per second has been produced. And next, so, and that's the experimental. And again, where is it sitting, this concept? So we have the specific, more powerful and higher speed, and then the purple areas where the propulsion system sits, that it could have hundreds of Newton. You could produce hundreds of Newton given the power. Of course, it scales with power, and you could have higher specific impulse. And it's a complementary that you can achieve higher. And there is no limit to it. As I said, it's scalable with magnetic field. Next. And then, so the missions, so scalability is always come that you can actually go with short to long range space mission. So as I said, if it's low power, it could be solar. For low power missions, solar powered, it could be nuclear electric and nuclear fusion. That's what's in my heart. That's what I want it happens. And there are different missions. For example, it's you can go to the moons of the Jupiter, and if it's fission powered, alpha is an important parameter here, with a payload in a matter of few years. If it's fusion powered, of course, with a budget of 10 times larger power, you can actually do it much shorter time. So different missions are possible. Next, please. Oh, and this is a summary, which is that the reconnecting plasma drive is highly scalable, And so it's the first time that actually we are saying that we can get a specific impulse directly from magnetic field through this process of providing the helicity and reconnecting, fast plasma reconnection. And its compactness is really important because you don't want to have a complicated system, you know, with antennas of all the things carrying. So it's a simple components of it is important. And the fuel is also flexible propellant is important. And you can run with, you know, lighter gases, and scalability, of course, and it's patent pending. So for by Princeton University, if you want to license, you need to contact Princeton University. And one more thing, I'm getting that I should stop. That so it's also, so you can contact Princeton University, and this project is grant funded right now, currently at PPPL, and there's a couple also grant pending, but we currently, we've been talking to private investors, and please contact me for making this happen in reality. And thank you really for your attention. And my email should be there, but sorry about it, lastname@pppl.gov or lastname@princeton.edu. Thanks a lot. And I'm happy to answer questions.
Time for one question?
At least one, yeah.
Okay. So a lot of the questions that I actually got were answered in the course of the rest of the talk. So can you comment on the experimental challenges with realizing the fast magnetic reconnection? Are there any engineering benefits
I think
versus other propulsion methods?
Engineering benefit is the simplicity of it. The components that I show we have done it in the experiments. We have the proof of principle, so, and the compactness of it. The challenges is that it's been routinely done in the experiment, not for propulsion, of course, needs to be built. And I mean, challenges is that do we need to replace plates? You know, how often we need to replace them, you know, as you get, you know, these plasmoid formations. But it's kind of the magnetic configuration and it's electric, and the electric field, they are all, the fact that it's static is also important. But you can also control it in a way. We know how, we have done these things a lot. We know how to control plasmas through, you know, pulsing it and all of that, yeah.
All right, I think we're gonna have to cut off questions there, but we've got your email in case people have others. Dr. Abrahami, thank you so much for doing this. We appreciate it.
You. And I wish I was there. Thanks a lot for the invitation. Thank you. Bye.
All right, back to in person. Jeremy Dietrich is going to bring us home between here and lunch with looking at the worlds that are near us. So Jeremy, where do you? Thanks.
Hello, everyone. Hopefully I can get this all done before we go to lunch and ready for that. So this is going to be a little bit talk about my current research. I'm actually a graduate student here at the University of Arizona with Professor Daniel Apai, and we're looking at the orbital architectures of planetary systems in general, but specifically focusing on the closest ones within 15 parsecs. So we've heard a lot this weekend about, you know, traveling to other worlds, specifically using stuff like Breakthrough Starshot. But what we need to know, you know, we've always wanted to know where we belong among the stars. Can we find other planets out there like ours or similar to ours in some way? And can we eventually travel to these worlds ourselves? So, you know, we've started finding planets in the last 25 years or so. And you can see they start getting a lot faster as we go on. And then right about now, you get the Kepler Space Telescope. And so we're up over 4,000 confirmed exoplanets that we've observed across the universe, across the galaxy specifically. And this is a little image of some of the closest systems to our own. This is actually not fully updated. There's even more we found recently that would be within these volumes. But these are just, you know, a sample of some of the closest systems that we know to date. So I took a bubble of 15 parsecs around the solar system, and we know of 86 exoplanet systems. Now, there are roughly 1,500 stars or so in that bubble. So the fact we're seeing only 5% or so of the systems having planets, this is a very big caveat that these systems are the only ones that we know of. But we, from the statistics we have of all the other systems, there should be planets around almost any star, basically. So there's a limit of what we can do with our current technology on what we can observe. So quick little table. This is, let's go through this quickly, but there are 38 multi-planet systems. 19 systems are multiple star systems, and 6 of them actually have multiple stars and multiple planets. So from that list of 15 parsecs, which is just a little inside of 50 light years, there's a total of 108 stars in these systems with 153 confirmed planets. However, there are also dozens of unconfirmed planet candidates and countless missing or hidden worlds that we just haven't yet been able to discover. Also, many of these have hosted ET civilizations in science fiction, Alpha Centauri, Epsilon Eridani, Tau Ceti. And for some of these, like Star Trek, Star Wars, et cetera, they require faster than light travel for, ease of storytelling. Hopefully we don't need that quite for some of these ones in the future, but, you have the civilization video games taking you to Alpha Centauri. You have the generation ship from the Nauvoo from the Expanse taking you to Tau Ceti. But there's still a lot of challenges for, finding these systems that we want to travel to. There's a lot of unconfirmed planet candidates. Many of these planets are likely still missing just because we just can't detect them. Either they're too small or they're not orbiting at the right angle for us to see them with our current technology. So we also have no current way to travel there easily in ships that are sized for humanity. Breakthrough Starshot can get there, but in the next 30, 50 years or so, but microprobes. However, what we can do is study these systems, these exoplanet systems, as a whole population using statistics. So what I've been working on is the Dynamite Integrated Analysis of Planetary Systems. Dynamite is a acronym for the Dynamical Multi-Planet Injection Tester. So what we do is we take the specific incomplete data, all the data we can gather from an exoplanet system, periods, mass, radii, inclination, eccentricity, anything we can get from the system we can get, but it's usually incomplete. We don't have the technology yet to get everything. We can take statistical distributions and models that are gathered from large exoplanet populations, like the Kepler planet population. There we have enough information there that we can actually, predict what the likely systems would look like. So yeah, then we take these models and then apply them to the system that we have and the data we have for each system, and can actually predict the presence and additional parameters for other planets in the system that we cannot currently see. Now, all these predictions are of testable, observable parameters. So any follow-up observations, we can guide them and say, hey, look for these, signals or something like that around these periods, or what the radius would be and stuff. And we can actually prioritize these targets for follow-up characterizations. And so hopefully in the near future, we'll find enticing targets for these interstellar travel. So this is just showing what this thing can do. Originally, we took one Kepler system and removed a planet from it. It's the smallest and last found planet from the system. And Dynamite basically finds it perfectly. It says that there's expected to be a planet right there. And this is just based on statistics. It has no knowledge that there is actually a planet there, but it says based on the statistics of knowing there's planets E and D, it says we should find planet F. So obviously everyone's been looking at the Alpha Centauri system. It's the closest one to us. It has both the Alpha Centauri sun-like star and Proxima nearby. So I figure we're probably going there pretty soon. That's the whole idea of breakthrough starshot. We're hoping to get there within 30 to 50 years. It is a triple star system, right? So Alpha Centauri A is a sun-like star. Alpha Centauri B is slightly smaller. They orbit each other about 80 years. Proxima Centauri has a multi-hundreds of thousand year orbit that orbits the main binary. There actually has been evidence for planets around the main binary, around the stars in the main binary. Alpha Centauri B was thought to host a planet back in 2012. However, more recent analysis in 2015 essentially disproved that. There is possibly a gas giant companion at Alpha Centauri A that was just found this year with direct imaging. The method needs additional verification. They're not quite sure it's not instrumental, but it's very interesting because it might be near the habitable zone of Alpha Centauri A. However, the most well-known planet in the system is around Proxima. So there's a likely rocky planet orbiting Proxima Centauri in its habitable zone, temperate zone. The orbital period is roughly 11 days, but the problem with that is it's so close that there's likely tidal locking. So the planet has one side facing the star all the time. There's also high flare activity and high UV radiation from Proxima. It's a very active star. And so that could have problems with habitability in the future. There is an additional planet orbiting at the period of about 1900 days or 1.5 AU out near the ice line. It is not officially confirmed, but multiple different evidence for it have been found. So it is likely to be confirmed soon. And then just this year, there is another possible small planet found within the orbit of Proxima B at about 5.2 days. That is currently unconfirmed, but we'll still be looking for it. And so we can show, if we run Proxima Centauri through dynamite, that there is a likely possibility that D is genuine. There is a relatively high probability that you would find a planet there, given where the location of planet B is. You also might find an additional planet if you're considering the likelihood of where is the next planet in the system would be out beyond B and could be in the outer edge of the habitable zone. So we have support for that unconfirmed planet candidate at 5.2 days, and any additional planet would likely be at the outer edge of that habitable zone. Tau Ceti. This is the closest single sun-like star, since Alpha Centauri A is in a triple system, but it's slightly smaller and a little bit less luminous. And so, we would need a generational ship like the Nauvoo, or near light speed travel like you would see in something like Rama from Arthur C. Clarke to get there. I just really love this cover of the Raman node outside Tau Ceti. So Tau Ceti is thought to host at least 4 planets. There's been direct evidence confirming at least 4, and there's direct but weak evidence that's not yet confirming at least up to 4 more planets. There's also one additional signal about a period of 320 days or so that has been discarded as an alias of the Earth's orbital period itself, but that's important to note in the future. So this is the current status of the architecture. There's basically 7 planets within the inner system out to about 630 days, or just outside the habitable zone, and then there's an additional Jovian mass planet orbiting at about 2,000 days out near the debris disk. So if we look at the inner system, just the 7 confirmed and unconfirmed candidates, and we look at just the confirmed candidates, we find that there's support for each of the 3 unconfirmed candidates in the inner system. So each of those is likely to be genuine and would dynamically pack the system, including that one gap we talked about at 320 days or so. There is support for that might also be a genuine signal, which if it were would be a likely or possibly rocky planet inside the habitable zone of one of the closest stars to us. So update support for all the unconfirmed planets. Additional planet would likely fall near that 318-day signal. So here's another one. This is the GJ667. I say this is relatively low because it's about 5 times as far as Alpha Centauri, or 2.5 times as far as Tau Ceti away from us, about 6.5 parsecs. But it has 3 small main sequence stars orbiting it. There are 2 confirmed planets, but possibly up to 7 total orbiting the smallest star. They all have a variety of sizes, and at least one of them is in that temperate habitable zone area. So this is the orbital architecture given just consuming the 2 confirmed planets there. You can see that there's support and evidence for other additional planets. And I will cycle through adding in, we added in planet D here. If we add in planet F only, and then added only E, only, and then F and D, and you find that the positions of planets E and F are in those small pockets of stability between the other planets and candidates. So if there was likely to be a planet there, that would be the only place you could find it if those signals were real. So yeah, if all planets existed, the system would be dynamically packed all the way from the innermost planet B all the way out to G, and it would span the habitable zone. You'd have up to 3 planets inside the habitable zone. Unfortunately, the signals other than those for those planets B and C were recently found to likely only correspond to stellar activity. So there's only 2 confirmed planets. The other ones are controversial at this point. But if they were to be real, it would be a very interesting and dynamic system to search for. Finally, I'll talk about L9859. This is a system that was observed with BM dwarf. It has many planets close to the star, like Proxima Centauri. Again, about as far away as GJ667. But there are 3 known transiting planets that were found in 2019, and then 2 more another planet, another candidate were found via radial velocity just this year. And so they form a nice ordered chain all the way out to the habitable zone, and the last planet exists right where you'd expect the additional planet to be found. An interesting fact about this system is that planet B is only half the size of Venus. And so we have a large variety of planet sizes and masses that we could test here, and in the system we could really learn a lot from as well. And then so if we include planet F, it pushes another planet out directly into the center of the habitable zone. So looking forward, and I can get this done pretty quickly. As we know, 86 exoplanet systems within 15 parsecs. That we know of. There should be 90, we're missing 95% probably of the exoplanet systems. 153 confirmed planets, but there are dozens or even hundreds that are unconfirmed or controversial. And there are a significant number in that habitable zone. These are potentially habitable worlds based on a whole bunch of other factors that would need to be discussed. And since we're in development for the technology to send probes to these nearby systems, we can use dynamite to basically look for and characterize the best targets to send probes and eventually send humanity all the way there. So I'll end there.
So how many data points within a system are necessary to predict the full system? Could you, for example, predict a 5-planet system from only 2 known planets, or do you need more data?
Right. So currently we require 2 planets. Otherwise, everything is kind of extrapolatory. We're only would be accurate with 2 planets. But starting from 2 planets, you can run dynamite iteratively, and it finds the next most likely planet. So for example, with Tau Ceti, we had 4, and each one of those we could add up to 7. So yeah, you can start with 2 planets, and eventually, if you wanted to run it iteratively or to test certain hypotheses, you could find 4 or 5 planets and work your way up.
Does dynamite take into account planet mass? I didn't see any specific reference to that in the way that the algorithm works. And so I was wondering if you have, Jupiter-like Jovian planets that intermix as well with smaller rocky worlds that would change the statistical distributions.
Yes. So the mass comes in. I don't know if I can go back, but the mass comes in the graph by dynamical stability. So we ensure that systems are dynamically stable if we were to insert a planet. And so basically, if they come too close, there's a little, it runs a simulation to try to see whether or not the planet will get ejected. Currently, the population statistics are only accurate out to about Neptune mass planets. So we're only dealing with statistics of those. But yeah, Jupiter mass planets would definitely, if you had Jupiter mass planets near Earth mass planets, it would definitely become a bit harder to inject planets there because of the mass.
So is that how you get the different heights on those relative likelihoods, where you've got the really low height relative likelihoods near the 1-day period and the relatively higher at the 100-day?
Right. So the dynamical stability says near 1 day, it's yeah, there's the problem with planet B is right there. Also, you're so close to the star that the star itself, the mass of the star itself will also be having problems. And then there's that little bump, it's hard to see, between planets C and D. And that's because the masses of C and D are more than the mass of planet B and E. And so those are the hardest places to find one. If you switched, for example, the orbits of planet C and B, you might find more probability there at that smaller gap, just because planet B is a smaller mass and therefore would have more room to put another planet.
Oh, okay, and so that's what leads to the dynamic packing that you were.
Yes.
Okay, gotcha. Are you using any machine learning or neural networks as part of your predictive tool?
Currently, there is an option to utilize the Spock dynamic stability package, which runs machine learning on a small like integration of the system to determine the stability. That is one of the options we have. We allow for multiple different types of options for dynamic stability, the period distributions, the radius distributions, and stuff like that. But so right now, it's not guaranteed that machine learning is part of it, but if you wanted to run it with the machine learning aspect from Spock to determine the stability, then that's able to be done so.
Are you able to comment at all on like how much computing power this actually takes?
So if you use the simple dynamic stability model we have, this thing takes 15 seconds for any given system to run 100,000 iterations of the system and produce this sort of graph here. If you wanted to run something where you were using an n-body integration for every single one of those iterations, then I use a supercomputer cluster with hundreds of cores, and it would take a day. So anywhere in between those two, depending on where you want to set up your where you want to use the n-body integrations, that's the level of computing power needed.
Okay. Any other questions from the crowd? No, we got it.
All right, Jeremy, thanks very much. I appreciate it. Thank you.
Thank you.
All right. Good job. I'm not dismissing you to lunch. I'm dismissing you to the lobby where we're going to get a photograph. Is Chris still in the room? Yes. Chris, wave your hand. Chris is going to be on a balcony looking down. Walk past him, turn around, look up. We're going to have a photograph out there for everybody here. Yes, you have to be in the photograph. Thank you. It's something we've done at these for previous years. It's a great thing to show off the number of people and the variety that we get here. So please do participate in that. That's in the next 3 minutes. So head for the lobby, look for whoever's holding the sign, maybe me. Look up, smile, look pretty. You can take your mask off. And then I will dismiss you to lunch. Lunch is next door at the Graduate Hotel. That's the name. The Graduate Hotel, if you were at the reception on Friday night, it's directly across the street. If you weren't at the reception Friday night, just go out of the Marriott, follow the main street to the right, and it's half a block. You can't, even if it's raining, it's not far. Don't forget, we still have some tour slots available for tomorrow. Don't forget, we have Birds of a Feather dinner being created for tonight and for tomorrow night. Those clipboards are all at the registration desk. Head for the lobby, let's do a photograph, and let's go eat. Any questions? Anybody here from the media, come over to this corner and say hi real quick. So thanks.
Dr. Edward Ely received a PhD in plasma physics from the University of Wisconsin-Madison in 2003. Her research interests span from magnetically confined fusion plasmas to flow-driven plasmas such as accretion disks. Her primary research experience has been in the field of theoretical and global computational extended magnetohydrodynamics with wide astrophysical authority.
Fatima Edward Ely, welcome to the program.
Thank you for having me.
Thank you recently wrote a paper detailing the propulsion system that like to process really expand the solar system because greater speeds are possible with this and with that greater solar. Could you give us an overview of how the system works at most basic?
Yes, so this is basically the cluster concept. Way to actually access that much very high application based on the magnetic process. So it basically uses spectrum mechanism to put high velocity, and that's the process of magnetic information. So what you can see that basically the rocket concept so much shape plasma gas, back of the rocket, and that's basically the basic mechanism you see, like molecular type, which is the energy. What happens we know that sun is basically a huge magnetized natural experiment. We call it luminous, but that is we love our sun because it's so magnetized. So there's a lot of magnetic energy built into that. So the process is that the process of magnetic intro to that is what actually visible in mind. Actually something solid like or the still line basically that they are and then you put it on the surface of the sun for the proportion of the sun. And then still line the stars. And I'll see them actually twist that, and that's when the process of magnetic information happens. And that's the conversion of the magnetic energy to kinetic energy, and that's what the trust concept. At these locations, we call it reconnection sites. The opposite direction they come together and then we call it exon. That's where the field is kind of zero kind of have the concern of energy and energy will become and agency is that basically based on the observation, we know that each object, each eruption happens of the sun. So the structure and also the fact of particles, it basically expels pretty fast compared to how the observation. So this is nature says that I can make this kind of velocity for it based on the process of magnetic information. And that's the fundamentals of this really trusted concept that I would say that using this concept of the information that to accelerate velocity.
Now, what kind of speeds are we talking about as opposed to how much faster can you go? Say?
Yes, great question. So there are clear chemical rockets. We know that they kind of launch from Earth to And also something called specific heat pulse, which shows that fuel efficiency for chemical grade, 400 seconds, we could just say. And so you kind of need a lot of fuel to basically for these rockets to operate at the long distances. Thousands of tons you can say for them to be actually operating, and also it's not really practical for the long distance travel space. And with the amounts depending on thrusters that they are not for in launching from getting out of the gravity. That is what they actually build those thrusters. Those are the different types. Again, they have kind of some limitations. Not be able to get kind of high velocity, velocity. They can get to tens of kilometers per second. But there are some limitations for function. You can have velocity, you can have and they don't use magnetic field efficiently because this thruster is saying that you need kind of magnetic connection to kind of be efficient because for the process, again, they have to get back that it's not magnetic bubbles or rings of magma being required. So they are born, as being born, they are attached. That's really unique in this process, that they are continuously, spontaneously are born. This is these bubbles, but also connections bubbles, they are kind of born and attached. Very they don't use this kind of that's the magnetic connection. So we device that also with the kind of self-pulse. So the external pulsing for the magnetic connection and also for the magnetic device or part of the self-pulse. So I would just say that yes, basically self-pulse and also produce the velocity. So it's not that we use mechanism to kind of make this kind of velocity that it's long distance from the earth that don't need to connect and also beyond that. So, and the idea actually when you mentioned fusion to my background is fusion, but I have to but I want you to just integrate some of these current information, the current startup information, experiment we have in Princeton in national experiment. So I kind of came up to this, I kind of saw this, how these fast magnetic connections can produce this kind of objects. And then when I just basically the side effect of that study was that, oh, I can use this actually for trust because it's objects.
Oh, I did scripts for you.
What, okay, come here.
What? Okay, here I am. Oh, yeah. Oh, you can hear me. How do you turn that off? To do what? I don't know.
Okay. Little last minute shuffling of slides, but we're doing okay. If y'all over by the door can grab a seat. Yeah, let me get this Brian McConnell. Shh. I know it's hard to shut this crowd up. Anyhow, thanks for excuse me. Thanks for participating in Brent's conversation over lunch. He really wanted that to be interactive, and y'all lived up to it. So thank you. I appreciate that. Back to plenary. We've got back to back. We've got a bunch left this afternoon. Some great material coming up. And the first one is Brian McConnell asked the question. So said he found something. Now what? So that should be fun. Over to you.
Hello, my name is Brian McConnell. I'm a software engineer. Started out my career working on telecommunications systems, and nowadays work a great deal with translation technology. I've also written 2 books about SETI and a number of scientific papers. My area of interest is mostly about what would happen if SETI detects an information-bearing signal. What would the sequence of events look like? And what types of people would be involved in the effort to analyze and comprehend the contents of such a transmission. Slide. So SETI, as you know, has been running for about 60 years, starting with experiments at the Green Bank Observatory. And is now more or less running continuously, looking for signals in both the radio and optical bands. There are groups at Berkeley, the telescopes in both hemispheres. Sorry, I'm getting a little bit nervous. And the people involved in these programs are, subject experts, radio astronomers and optical astronomers who are specifically working on searching for, artificial signals, operating at remote sites, often with limited connectivity. And, the SETI can basically be characterized as a project with a low probability of success, but if it succeeds, it'd be very high impact. A good analogy is an Earth impacting asteroid. It's very unlikely to happen in any given year, but if it does, would be very disruptive. So just like everybody to imagine, one day we wake up and one of these searches has found something, or it looks like something. This could be an artificial radio signal, or it could be an artificial optical signal. So, optical signals they search for are very brief nanosecond pulses that can briefly outshine the star behind them. Now, at first, we won't know that it's artificial, especially if it's a radio signal. One of the problems with radio SETI is that they detect millions of candidate signals all the time, but they're detecting our own technology. So discriminating between an actual alien signal and one of our own satellites or a ground-based transmitter is very difficult. And in fact, to date, we've had a couple of, I guess you could call dry runs, where we found something that looked like it could be an extraterrestrial signal, but it turned out to be human generated. So this process could unfold very quickly in some cases, or it could drag on for years in others. So a good example is the Breakthrough Listen Candidate 1 signal that was detected by the Parkes telescope. At first, it passed all the tests, looked like it was originating from outside the solar system, looked artificial, but it was a transient, was only observed once and for a relatively brief period of time. Or actually, it was observed on several runs, but it was only observed for a limited period of time and was only observed by one telescope. So that made it very difficult to confirm. So it looked like it could have been an extraterrestrial signal, but after a long period of analysis, the consensus is it's most likely human-generated signal. So in that situation, there could be a great deal of debate and discussion about, is this really an alien signal or not? And it might never become, agreed on. Another good example of a signal that meets those characteristics is the WOW signal that was picked up back in the 1970s. And on the other end of the spectrum, with the optical signal, that could be confirmed as extraterrestrial very quickly, perhaps in a matter of days. The reason for that is there's much less background interference to contend with, and that kind of signal is pretty unambiguous and doesn't look like anything we generate. So if you had a situation where one of the optical SETI programs detected a blinking pulse coming from a nearby star and observed it from 2 or more telescopes, you would know pretty quickly that we were looking at an alien signal. So at that point, once that's confirmed, that's about when the announcement goes out and the whole world is like, holy crap, oh my God, aliens. And then we proceed to the next step in understanding what we're looking at. And that's the signal analysis. What we want to know in this stage is the signal engineered to encode information? There are many ways to encode information on an artificial signal. So in the optical band, you can modulate the wavelength or color of the light. You can modulate the duration of each pulse. So for example, if you have 4 different pulse lengths, you could encode 2 bits of information with the pulse duration. The interval between pulses, that's also something that can be modulated. And the polarization of the light. So, just with each pulse, you could probably pack 8 or 10 bits of information. And then, let's say you're pulsing 10 times a second, you can transmit 100 bits of information per second. Now, by our standards, that's a glacially slow communication channel, but that works out to several gigabits of information per year. So you could actually be receiving a decent amount of information. So at this stage of the process, the number of people involved would expand greatly. So anybody that's experienced in communication systems design, wireless communication and networking, anybody with that kind of expertise will be able to participate in this stage of the analysis and comprehension process. So it wouldn't just be SETI engineers at this point. You can imagine pretty much every electrical engineering department in the world would be interested in looking at this. And so and then the end product or the output, data product from this stage of the analysis pipeline is you basically start reading out signal states. Now you have no idea what these signal states represent. Maybe it's binary code, maybe it's something else. You have no idea how it's structured. Is it just one long sequence of signal states, or is it, are we looking at n-dimensional data structures? Could be anything. And this is where things get really interesting. Because once you start reading this data out, for one, it's not a huge amount of data. I mean, we're not going to be getting gigabits of data per second, at least at first. So you have a relatively small amount of data that can be distributed. And basically anybody with an internet connection and a computer and a hypothesis to test will be able to participate in this stage of the process. So, this would be a globally distributed effort to understand the contents of the transmission. It would involve both professional and citizen scientists. And one of the things that's interesting here, and this is, it's just an interesting thing with computer science in general, a lot of the most important contributions in CS, are the result of individual contributors or very small teams of people within larger organizations. So I like to cite the example of the Python programming language. It's widely used. It's used in some of the biggest, internet systems in operation. And Google, for example, is heavily dependent on Python. It was written by one guy, Guido van Rossum, in Holland back in the 1980s. So it's quite likely that most important contributions will come from people who are not involved in SETI. And it really could come from anywhere. It could be, somebody within a university, could be, this is a random math whiz somewhere in, South America. You just don't know, but that's what's interesting because there's so many things that you could, we really have no idea what would be, within the transmission in terms of content, so being able to try lots of different hypotheses, will enable us to, speed up the process of understanding what's being sent, if there's an intent to communicate. So what do we need in terms of information infrastructure to support this? Well, an interesting thing with study organizations is while they excel at processing huge amounts of data, petabytes and more, they're not set up to handle large numbers of users, because one of the things that will happen if there's a contact event is huge numbers of people will want information about, what have we found? What are they saying? What are their intents? So this system will have to, scale to handle millions of concurrent users. It'll need to be resistant to denial of service attacks because anything related to SETI will be a very attractive target for hackers. And it'll need to have what's called a revision history. So if one of the input sources to the system is corrupted or compromised, you can roll that back. And the operating cost should be minimal while the system is in standby mode, but then scale with usage. Now, the good news is there's several cloud-based services that meet most of these requirements. So if you were going to build it today, it'd probably look like some combination of Google Compute System or Amazon Web Services, and then there's source code repositories like GitHub that would work very well for this. So I like to call this the interstellar communication relay. And it's intended to be sort of, comparable in functionality to the deep space network, but largely based on cloud-based computing resources that are highly scalable and don't cost much to operate. So this system would, be intended to support, several different user communities. So, on one end of the spectrum, you'd have, highly technical people that were, signal processing experts that are looking for additional carriers or looking for additional modulation schemes. And then on the other end of the spectrum, you'd have less technical users, and they would be looking at derived data products. So, for example, imagine that there are uncompressed images or bitmaps interleaved in this transmission. And there's many different things that could be there. I'm not saying that there necessarily would be, but one of the things that would happen then is somebody somewhere would write a program to extract those images and convert them into a format that non-technical users can look at. So like PNG files, GIF files, that sort of thing. And so one of the other things that's interesting about this is as we start to understand the structure of the data and the different media types that might be represented, a broader community of people will be able to participate in the analysis process. So, imagine again, if they're images, the images could represent anything. So you might have images of structures or buildings. So you could imagine archaeologists and other types of people looking at those images and trying to understand what they represent, and they wouldn't necessarily need to understand image processing software. So, and then I'd just like to wrap up with a few comments about risks. Originally, I was going to talk more in the front of this about the risks associated with SETI. A lot of people assume, or sort of widely assume, that passive SETI or listening is a low-risk activity compared to transmitting. I would argue that's not true. Passive contact can be highly disruptive. John Traphagen gave a great talk here a couple of years ago about what happened when Commodore Perry sailed into the Tokyo harbor. The Japanese at that time had never seen steam-powered ships, and it upset the whole social order, because they realized everybody else, the rest of the world had advanced greatly over a period of several hundred years of isolation, and really caused a great deal of disruption to their society, and some would argue ultimately led to World War II. I think one of the big risks is that contact will attract a rogues gallery of con artists, about 30 or 40% of the population is already primed to believe that UFOs visited us and aliens exist and have been here or are here. So there's going to be a huge audience of people who are going to be primed to believe people who present themselves as being ambassadors or otherwise somehow representing another civilization. There'll be a lot of money for those people to make, and there'll be a lot of people who will be happy to give them money. And this distinguished gentleman in the picture here, that's the Reverend Jim Jones from the People's Temple in San Francisco. He's been dead for quite a while now. He took about 800 people with him. And it's likely, I think, or almost certain, that there are people like him that will surface, in the wake of a contact event. And we need to be prepared for that. And one of the ways we can be prepared is to have adequate information infrastructure so that whatever we're receiving is comprehended as best it can, as quickly as it can, and that there's a trustworthy, reliable source of data that people can turn to, as well as the interpretation of that data. Pardon? Well, no, Jim Jones, he led a cult. I'm not following you. No, I'm just saying that, this kind of charismatic personality is, that's the type of thing that we're probably going to see is, people will surface that will, defraud people, create cults. And, especially if there's any ambiguity about the information we're receiving, people will be able to present themselves as having, special access to the aliens, or saying, hey, the government knows what's coming, but, they're not telling you, but I will. And there'll be a lot of people that will fall for that.
Thank you, Brian. We have several questions. First, what is SETI's policy if they think they found an ET signal? Do they notify/clear with government prior to public release?
So there is a protocol. It's voluntary, so it has no force in law. But all the SETI organizations, have signed on to this. So basically, they'll make every effort to verify that the signal is real, and then the team that made the discovery would make an announcement. Now, they're going to be very reluctant to jump the gun on that, because nobody wants to call a press conference saying, hey, we've made contact with aliens. And then 2 weeks later, come back and, about that signal from aliens. Well, we detected a microwave oven in our break room, so.
Thank you. And finally, could spread spectrum broadcasts be distinguished from noise without knowing the details of the spectrum spread characteristics?
So I wouldn't know the answer to that question. I'm a software guy.
Copy that.
Thank you.
Good job. Thank you. Good job. All right, up next, we're going to be swapping between in-person and Zoom again. When the program committee selected the next paper, it was written by Matt Wenzel Long. And we accepted it, and then Matt was not able to even participate by Zoom right now. Luckily, his co-author, Jeff Landis, was already accepted for a completely different paper, which you're going to hear in about 40 minutes. But anyhow, Jeff Landis is on the Zoom, and he's going to present Matt's paper, then his own a little bit later. But Jeff, if you can confirm you're online, I'll give you the mic.
I am online. Can you hear me?
There we go. Can hear you. Thanks.
Well, thanks. Yeah, I would like to start by acknowledging my co-author, Matt Wenzel Long, who did the computational work I'll be presenting, which is sort of by far the lion's share of some of this work. So thanks a lot, Matt. Good work. Yeah, I guess I have to tell you to click. Next slide, please. We're talking about the question of power for an interstellar probe. So as we know, several people are looking at the idea of ultra lightweight interstellar missions that could reach Alpha Centauri in as little as a 20-year interstellar cruise at 20% of the speed of light. But next slide, please. The difficulty here is that these are extremely lightweight missions. They're essentially chipsets. So how do you do anything once you get there if your payload mass is measured in grams? And there's many aspects to the question, how do you do anything? We just heard a paper talking about how do you communicate? Well, one of the problems is power. How do you communicate needs power. How do you make sensors? What do you do once you get there without power? So the power source for this interstellar microprobe is just an extremely difficult power system. Nobody has something that can produce the amount of power needed within the mass limits. Next slide, please. The baseline system we looked at was something very much like Starshot. And thanks to the Cornell people for showing off this little chipset. That would be the type of payload that we'd have. The payload would be about 3 grams. And in fact, you accelerate it up to 20% of the speed of light at 15,000 Gs. So you need a relatively robust system. Then you have 20 years to wait before anything happens. And then you spend roughly 5,000 seconds flying by the planet. Next slide, please. So this is what we're looking at. Well, we need power for a lot of different things. The driver that we decided to look at was the power for data return. We were assuming some sort of laser communications. We were assuming probably we could continue to downlink for a year after the encounter, but we might need higher power for a brief time. And we basically assumed that the power requirement was in fact an energy requirement. So for this study, we made a straw man energy requirement of 300 kilojoules. Next slide. There's a lot of different approaches to power. In fact, back in 2019 at the Wichita workshop, I gave sort of a summary of these approaches. Weight is the critical parameter. So this particular work is looking at generating power from moving through the plasma and magnetic environment of the target slide, of the target star. Next slide, yeah. So specifically, we're looking at, can we generate power from the motion of the spacecraft through the ambient plasma and magnetic fields? And we looked at this both in the interplanetary environment, as we did the encounter, and also in the interstellar environment when we're just cruising through free space. So the question is, can we get something on the order of 300 kilojoules? Next slide, please. So the voltage induced in the passage through the magnetic field is simply the V cross B potential. We actually also looked at the idea of perhaps we could get power out of the kinetic energy of the incident protons and electrons. That turned out to be pretty difficult. So we, after a while, homed in on the idea we can use the magnetic field of the target star. So next, yeah, click once. There's a B field. We have a velocity. V cross B gives you, next slide, a E field. That induced E field, click one more time, please. The E cross B, B field gives you a basically an electric field similar to an electrodynamic tether. Next slide. The current, however, needs to be closed. We can't generate energy just from an electric field. We need to pass current. All current flows in a loop. You can't have one-way current flow. So the way we close the current loop is to capture electrons from the interplanetary medium. At the speed we're traveling, the protons will move right through a thin sail, but the electrons can be captured. So those electrons are captured. Then by some sort of cold cathode emission, we can eject those electrons at one end of the sail. You might ask, well, what happens if the medium is not ionized? Well, it turns out that's not really a problem. At 0.2 speed of light, the neutral hydrogen will be stripped to be electrons. So it will be ionized, whether you want it to be ionized or not. So next slide. So here's a view of what the magnetic field of stars actually looks like. I always sort of pictured magnetic fields as dipoles, but in fact, as Parker told us back in the 1950s, in fact, the magnetic fields spiral around the stars. Next slide. So it spirals around because the solar wind is ejecting particles. These particles spiral around the electric field. As the sun rotates, the motion of the moving particles sort of winds these magnetic fields around the star in this Parker spiral pattern. Next slide. So we scale this in spherical coordinates. Conveniently, we scale it from the B field at the Earth, and then we've calibrated it with Voyager 1 and 2 data that gives you the radial portion. So you then have the solar wind moving outward at a typical velocity of about 400 kilometers per second. You can fit that to give you the number of electrons per cubic centimeter. Next slide. Turns out the power is now proportional to the current times the voltage. The voltage is proportional to the V cross B potential, but the current is going to be proportional to the area. So the result is that the power is proportional to the length, the characteristic length cubed, or if you prefer, think of it as area to the 3/2 power. So we're normalizing all this power into units of power per unit area per unit length. Comes out in those odd units of watts per cubic meter. Next slide. So here's a typical graph. This is now coming into a planetary system of a sun-like star. The word sun-like star means we're assuming that the magnetic field and the plasma density is exactly equal to the sun's magnetic field and energy density. You're coming in from the right. On the rightmost slide, you see us moving from 120 AU into 20 AU. Then on the leftmost plot is the little bit further in from 20 AU down to about 2 AU. You can see that the power rises extremely quickly as you get close to the star, where both the magnetic field and also the density of the plasma rises, but it's still measured in fractions of a microwatt per cubic meter. Next slide. Next slide looks into Proxima Centauri. Turns out Proxima Centauri looks a lot better. It's a pretty dim little red dwarf star, but turns out red dwarf stars have powerful magnetic fields. Who would have thought? And they put out a moderate amount of solar wind. So now we're looking at something where as you come in from infinity, the power raises to levels actually of milliwatts per cubic meter, not merely microwatts per cubic meter. But now let's look at that actual flyby of a putative planet. Next slide, please. Here is a graph where we show a flyby at a distance from the star of about 1 astronomical unit. And this now depends a little bit on what angle you come in, both the angle from the planetary ecliptic as well as the angle from the magnetic equator. I'll look at that in a second. But this is the sun-like star. You can see for that critical distance when you're passing the star, actually power drops to near zero just for a second as you reach the point where you're moving parallel to the magnetic field, but you're getting power that comes up to a peak value now of about, maybe 12 microwatts per cubic meter. Just for reference, a Starshot solar sail circular with a diameter somewhere on the order of 4 meters, would have a R cubed for the sail coming about 50 cubic meters. So multiply that by 50 to get power for a starshot size sail. It's still pretty small. It's still barely coming up into the milliwatt level. Next slide, please. Looks a lot better, oddly enough, if we're looking for a 0.5 AU flyby of a planet of Proxima Centauri. Now we're getting power in that critical distance, about 0.5 AU to negative 0.5 AU passing the star. You're getting power up a maximum of about 30 watts per cubic meter. So the average power over the traverse is about 15 watts per cubic meter. Multiply that out by the size, and you might get a total power coming into reasonable numbers, multiples, maybe 15 watts or so over the distance. This one is just that angle to the magnetic equator, depending whether you're coming in along the pole or whether you're coming in along the equator. Turns out if you come in polar, that 90 degrees, you're going through fewer magnetic field lines, but you're always crossing those magnetic field lines at nearly a perpendicular radius. So it turns out it isn't actually as much of a factor as we had thought. The angle to the magnetic equator is not particularly a major factor. Now, I do need to mention that stars change. They have both magnetic and plasma events. So the solar wind is not a constant at about 9.5 per cubic meter. It goes way up and down. The magnetic field also goes up and down. And this goes even more so for the little red dwarf stars, such as Proxima Centauri. Proxima Centauri has orders of magnitude change in the plasma density as it goes through active and inactive phases. Moving on to the next slide, we can also get some power during cruise from the probe's motion through the ambient interstellar medium, depending on which way we're going, because we have to cross magnetic field lines. But the magnetic field in the interplanetary medium is non-zero, so we can get some power. It depends where we are. Turns out the sun's embedded in the local cloud, somewhere between 0.1 and 0.2 partially ionized hydrogens per cubic centimeter. If we're going to Alpha Centauri, unfortunately, we're going the wrong way. We're leaving the local cloud. We're going to a place where the density is more like 0.001. 0.05 hydrogen ions per cubic centimeter. So next slide. So the amount of power that we get is going to depend on which way we go. But for a circular sail cross section, multiplying out by that A to the 3/4, if we need 10 milliwatts, just as a arbitrarily picked number, depending whether it's the high or low electron density, it's from 5,000 square meters to 12,000 square meters. That would be sails of 82 to 124 meters, assuming that you're moving across the magnetic field lines. So just sort of a final slide, some of the conclusions. The ultra miniature flyby spacecraft requires a power system that's extremely hard. It's orders of magnitude lighter than anything previously made for a spacecraft, and it's really not a solved problem. There's a number of different approaches. We looked at one. There were some plausible approaches that say it might be possible to do these power systems, but it is by no means a solved problem. And I should point out that this was just the power generation portion we were looking at. Generation is only one portion of a power system. We'd also have to look at power storage if needed, power conditioning, power transmission, etc. So a brief summary of the work we did. I can stop now and answer any questions. Thank you.
So we have one question here. Can this method be used to slow down the sail? And if so, how much deceleration would you be able to get potentially?
Yeah, it turns out not. It turns out that the force that you're generating from these low density particles is way too low to make a noticeable change in your trajectory. As a couple of people had pointed out in years past, if you have a big magnetic field, you might be able to slow down in the ambient plasma. But typically to do that, you're talking essentially cross-section areas of many square kilometers to gather enough of that very tenuous plasma to slow down. The sails on the order of several square meters just is not good enough.
Thank you. And I had several questions, but you answered them in your last couple slides, so I think we're set.
Okay, great. Thanks. Thanks, Jeff. We'll see you again in about 20 minutes. Thanks very much.
Okay.
Appreciate it.
Thank you.
Thanks. All right. And up next is going to be live and in person is General Pete Worden, who I've seen this morning. Oh, there you are. Sorry, you were over there earlier. I was looking desperately in the other side of the room. So great, Pete, come on up. As Brent Ziarnik said during lunch, those of you who are on Zoom didn't get a chance to listen to our lunch talk, but Brent talked about how Pete has been a leading figure in this area for a long time. We're very fortunate to have him, former general, former director of NASA Ames, and now running Breakthrough Initiatives. So Pete, over to you.
Thanks.
And also a very generous patron of this event. So again, thank you for that as well.
Well, thanks. You thank my sponsor. He's the one with the billions of dollars.
You spend them well.
Really pleased to be here. And I want to, nobody else has done this. I'd like to thank the organizers for a superb conference. So maybe we could have a round of applause. Well, what I'd like to do is give you a quick summary of where we are with the Breakthrough Starshot. We've had a couple talks that go into a lot more detail and a lot more technically competent than I am. So if you have any detailed technical questions, I'll refer you to my colleagues. I'm not going to go into much detail of our organization, but basically the Breakthrough Prize Foundation was founded about 11 years ago. Our primary objective is to encourage scientists by making them movie stars. And to do that, because we're sponsored by a number of billionaires, is we have the world's largest science prize. They're $3 million each. There's 7 of them in life sciences, physics, and mathematics. This is about 3 times larger than a Swedish prize I'm not supposed to mention. I'd much rather win the Breakthrough one. Actually not, but that's, I'm not likely to win either. At any rate, there used to be a ceremony at NASA Ames, which has been postponed the last couple of years, but hopefully we turn up again. And it is sort of called the Oscars of Science. It's about the only time that you'll see scientists in a tux. And even less likely you'll see billionaires in tuxes. We had a few years of trying to persuade people like Sergey Brin that black tie doesn't mean a black t-shirt, but we're getting there. At any rate, I do want to cite one winner. This is Jocelyn Bell Burnell. She was the discoverer of the pulsar, but that Swedish prize was not given to her; it was given to her advisors. So a couple of years ago, our committee decided to grant her a special breakthrough prize in fundamental physics. To her incredible credit, she gave the $3 million to a fellowship for underserved students and women. A really great person. So we were able to kind of address an old sort of slight. I won't go into a lot of other things here, but just get right on to the breakthrough initiatives. Our sponsor of the breakthrough initiatives is Yuri Milner, a physicist, an Israeli citizen. And these were announced in 2015 with Stephen Hawking, who was our principal science advisor until he passed away a few years ago. And they're really all about addressing these three fundamental questions. Is there intelligent life elsewhere? Is there any other life in the universe at all? And can we travel between stars? Now, I usually have a kind of a smart aleck comment about intelligent life. And when I'm asked about this, I say, it's more likely to find the further are you away from a national capital. So, and I stand by that. At any rate, the first program we started was Breakthrough Listen. And, you know, it's this has been a very exciting program. It's $100 million US. It's managed through the University of California at Berkeley. And we have basically time on most of the world's large radio telescopes and a lot of the large optical telescopes to look for technosignatures. And I won't go into all the details other than saying we're using both space and ground systems. Probably the most significant ones on here, we've just started a research project with the Chinese 500 meter. You can see it in the bottom there. Probably our most significant new project is with the Meerkat, which is the first part of the square kilometer array in South Africa. But I'd like to talk a little bit about this instrument. This is the Parkes Radio Telescope in New South Wales. It's I think 63 meters in diameter, 64 meters. It's a very iconic radio dish. It was actually used to receive the Apollo 11 moonwalk. And there's a really delightful movie called The Dish. It's a family-friendly movie. You can take your mother and children and everything else and go see it. I even showed it to my wife and she liked it. But at any rate, a little less than a year ago, actually turned out to be Halloween. I got a call from Dr. Andrew Simeon, the PI for our Breakthrough Listening Committee, and he said, we have the first signal that passed our basic test. And there was interesting discussion earlier about what happens when you have a signal. Now, we wanted to spend a couple months, kind of figuring out, is this real or not? We designated this the Breakthrough Listen Candidate 1, BLC1. The really interesting thing is it came from Proxima Centauri, or appeared to. And, the very nearest star that we know has an Earth-sized planet in the habitable zone, not much more about it. But this was at, some, 950, 980 megahertz. But the signal drifted, as you would expect from a signal outside the Earth. It's a very narrow band. It was when we moved it off the telescope off the position, it disappeared. So we were quite excited. We said, well, we need to do a lot more tests and look at the instrument. This was, by the way, the instrument where the microwave oven was at one time, used by the team. And over the next, first of all, it only took about 2 or 3 weeks before somebody leaked it to the press. And so we ended up kind of prematurely at least having to say something about it. But over the next couple months, we looked very carefully at this signal. We're virtually certain, not quite 100%, that it is terrestrially caused interference or human caused interference. We did find some other signals like it, and they also showed that when you move the telescope slightly off and on, they were still there. But at any rate, this enabled us to exercise all of our procedures. And there are 2 papers that are I think they're going to be published in the next few weeks in Nature Astronomy on this. A very exciting effort, and it's I think that it's very instructional to look at this as an example of. I think it was handled very well by the team, and we didn't, at least to date, get a huge amount of kind of foolishness, but that's certainly a possibility. Let me talk about Alpha Centauri because that's our target, and give you a little update on where we are. Just to remind everybody, there are 3 stars in the system. Unlike the 3-body problem, they are not in chaotic orbits. But 2 of them are solar type. They orbit with about 80-year period around each other. The third one is noted as Proxima Centauri. It's a distant star. I think it's tens of thousands of astronomical units away, and it's a red dwarf star. of course, this is an artist's conception of what they look like, although somebody pointed out to me, it's amazing that all 3 stars have the same sunspots on them. We'll get it fixed. At any rate, that gives you the kind of relative size. So we had a program we started in 2016 called Breakthrough Watch. Was to see if we could find a life-bearing exoplanet, particularly in the Alpha Centauri system. Now, it turned out that we made this announcement in early 2016, but then in August, just showing it sometimes better to be lucky than good, the European Southern Observatory announced there was a terrestrial-sized planet indirectly detected orbiting Proxima Centauri. They were nice enough to invite me to the press conference. We were nice enough to give them $3 million to go do an instrument to see if we could actually detect other planets in that system. And of course, they have this picture, so I guess we don't need to go there because we know what it looks like now. But at any rate, this is the instrument that we decided to use. This is the Very Large Telescope in Chile. And by the way, as an astronomer, I have to say I'm embarrassed with telescope naming. Surely, Very Large Telescope, you could have found a better name. Now, it gets worse. It turns out that they're building a new telescope, which is 39 meters in diameter, called the Extremely Large Telescope. And no fooling, it was originally called, when it was going to be like 70 or 80 meters, the Overwhelmingly Large Telescope. So if any of you have a penchant for naming, go talk to the astronomers, they need help. At any rate, we had 100 hours of time with an instrument that we and the European Southern Observatory built for the number 4, which I think is the one on your right, that had a laser guide star. Infrared coronagraph. It turns out at 10 microns, the contrast between the planet and the star is maximum. It's only like 1 part in 10 to the 6th. So we have a maximum chance of seeing it. Now, I put this picture up. Probably a lot of you are science fiction geeks like I am. This is from Avatar. And to remind everybody that the scenario there is a giant planet orbiting Alpha Centauri A in the habitable zone. This is the biggest star that has a bunch of moons, one of which is not only inhabitable, but inhabited. And it turns out that, by the way, the giant planet is called Polyphemus, which was a cyclops. And we have a tentative detection of a giant planet orbiting Alpha Centauri A. So we might have discovered Polyphemus. It was considered interesting enough that Yuri Milner got in touch with his friend James Cameron, as he was, and so as he was filming the next set of the Avatar movies, he did at our annual Discuss conference, he did a real tour de force. It's online of the technical discussion. And by the way, to get to Alpha Centauri, he used a combination light sail and fusion system, so probably not too far off. At any rate, I'd like to sort of discuss a little bit here for the next few minutes, Breakthrough Starshot. This is the effort to actually get us to Alpha Centauri sometime later this century. The objective, just to remind everybody, is to launch in the middle of the century, go 20% the speed of light with a very small spacecraft, and go to the Alpha Centauri system. The way to do this, and this was announced, by the way, in 2016. This was Stephen Hawking's last trip to the US. We announced it at the New World Trade Center. And in fact, by the way, I can go back to that picture. There's a lot of notable people on the stage there, except for the guy on the far right. But Freeman Dyson, who just passed away not too long ago, was there. Ann Druyan, who's the creator of Cosmos and Carl Sagan's widow. Avi Loeb, who you heard earlier today, and Mae Jemison, who runs Interstellar organization, and then this geeky guy. But this was a pretty cool effort. The big question is, can we in a half century or so go 1,000 times faster than we can today? We point out that in the mid 20th century we did that. Can we do it now? And of course, the initial look was not very positive. By the way, if you want to know the guy see the guy back there with his hand on in the corner, that's Pete Klupar, our chief engineer. This is his chart, he's the one that had the original idea that this is very hard. But it turns out there is a way to do it. And again, these are our objectives. We need to go at 20% the speed of light, and to get there in some reasonable amount of time. There is an idea how to do this. It's very old. Kepler wrote to Galileo in 1610 that we should sail on heavenly winds. Now, we're not sure what he was intending, but we're going to say it's light sails. So the objective here is to get a really small mass, sort of Graham class spacecraft, leave the engine on Earth, attach this chip to a sail, and as you'll probably hear from other people, it's probably more likely the chip would be integrated in the sail than actually a separate chip, and use a very powerful laser to do the acceleration. Now, of course, light sails work. You've probably heard about some of the ideas of sun divers and so on to get to our outer solar system, but the sun isn't powerful enough. Chipsats are becoming real. This is Professor Zach Manchester at Carnegie Mellon. A few years ago, we worked with him to launch these chipsats. This is called Sprite. It's a 10-gram spacecraft. So we're, and by the way, if you have an electronic watch, the chip in that watch is very similar to a satellite. The laser array this is one of the big challenges, and we have 3 big challenges. Well, we have about 50, but we have 3 we're going to start with. The first thing is, how do you build a 200 gigawatt laser array as a kilometer scale for like $10 billion? So we have a major research program. There's, by the way, some very promising approaches. But if we want to go to Alpha Centauri, we'd like it in the southern hemisphere at high altitude. This is in the Atacama Desert, and this is an artist's conception of what it looks like. Now, I have to make a point that our sponsor pointed out, showing he is a physicist. He says, well, this is just wrong. I said, well, why is it wrong? He said, well, you're going to use 1 micron radiation, and you can't see that with your light or with your eye. And I said, well, Yuri, it turns out that it probably heat up some of the dust in the atmosphere and kind of glitter a little bit. He thought that was an artful enough dodge that I got away with it. But at any rate, a lesson I want to tell everybody, we made this announcement, and somebody asked us, well, where are you going to put this laser array? And we said, well, in Chile, in the Atacama Desert. Well, it turns out we didn't bother to tell the Chileans. So I was summoned to Chile. I had a wonderful opportunity to meet 2 different presidents of Chile. I bought them off with a star chip, 1 for each, but they've volunteered to be very helpful. So Chile be a good partner. You have something like half hour to an hour of laser illumination on a nanocraft that's 5-10 meters in diameter, that's deployed from a spacecraft in a highly elliptical orbit. We launched dozens, if not hundreds of these. And 20 odd years later, we fly by, not all at once. This is a National Geographic photo from their Cosmos stuff. But it does accurately show there'd be a lot of holes in the sail because there's stuff in interstellar space, so a lot of challenges. Now, we had some interesting discussions here just prior to this, and I point out that, that building the laser device for $10 billion is a big one. Building a sail that can take this much power is another one. Professor Harry Atwater is leading that for us. The third one is the communications, which Professor Phil Mauskopf, who talked yesterday, is sitting in the back, so he can answer technical questions. But the biggest problem seems to be the power for these systems, and so we're we've got an effort that Mason Peck and some of the other speakers here have been involved with. So I won't go into the details. I also want to point out that our sister organization, Limitless Space, is figuring out how to get people there. And Sonny White's here, and the Helicity leadership who talked yesterday. So I'm very optimistic we can actually get to the stars, initially with laser-driven light sails and eventually with people. I just want to close with we are looking at potentially private missions here in our solar system to look at these various locations. And my particular favorite is Earth's evil twin, Venus. We've just completed a study that we could potentially go to Venus in 2023 very cheaply. There's a private mission that Rocket Lab is looking at. There is tentative detection of some gases. So, and there's a Rocket Lab mission. So I'll stop there and be happy to take some questions, but all goes well here in about 50 years, we may have our first image of a planet orbiting a nearby star, maybe life bearing, you know, in the extremist, maybe civilization bearing. Unlikely, but possible. So I'd like to thank everybody. And this is the group that's going to take us there. So I want to thank you. Thanks.
Thank you. We have a question. What will Breakthrough Starshot do with the laser once it's done accelerating the spacecraft?
Well, that's a good question. And we're trying to look at that. Our view is that eventually this will get built by governments. And so it's not my problem. If we build the cheapest one, it's probably only going to be capable of sending things to Alpha Centauri, because the cheapest thing is have a fixed azimuth and limited range of elevations and so on that you can send this, and you can see the artist's conception. However, there's a lot of other really significant things a laser can do for light sails. I mean, we can send things all over the solar system, but you'd have to make it steerable. Now, there is a big policy issue, because, you know, if it's only going to Alpha Centauri, it has less worry of being, you know, some sort of nasty weapon. So we've begun policy discussions on use of lasers in space. We had a conference 2 years ago in the Czech Republic, and we're having another one, I guess, James, in November. And we've begun discussions with the UN Outer Space Office on how to come up with protocols of how you use lasers in space. But laser-driven light sails could take us all over the solar system very efficiently.
Thank you.
Oh, and by the way, they could protect us from asteroids. They're powerful enough at a few hundred gigawatts that we can blow away the surface material and accelerate an asteroid out of the way.
I think Jerry Purnell mentioned that once as a planetary defense. He said it's sufficient power, you just raster scan the asteroid.
That's right.
Pulverize it. So another question, or?
Oh, yeah, we do have one more.
One more.
What was the space telescope shown in the center slide on the assets Breakthrough Listen is using?
TESS. That's the TESS Planet Finder. We did a joint program with TESS to look at Proxima Centauri. Indeed, it's the data from that showed BLC1. So it's, you know, they were looking at, you know, seeing if they could see eclipses and other things. And so it's, we've also looked at other objects that they're doing, but it's a neat mission. Almost as good as the Ames mission, Kepler.
Thank you.
General Warden, it's a pleasure. Thanks so much for having me here. We appreciate it. Thank you. All right, we're bookending General Warden with Jeff Landis. He's coming back on Zoom with a discussion of bustered ramjets, which we probably have all heard of, and I think he's going to disappoint us a little bit, but that's okay. Jeff, take it away.
Okay, well, good afternoon again. I'm going to talk about an idea a little bit further out, Robert Bussard's concept for a fusion ramjet for interstellar flight. And I should start out by saying that there's a poster presentation by Al Jackson and Peter Schatzschneider, the Interstellar Ramjet and Engineering Nightmare, which covers some of the engineering issues that I was just going to gloss over. So I'd urge everybody to go check out the poster and go talk to Al if you have questions on his end. Next slide. The Bussard ramjet is, of course, beloved of science fiction writers. The whole difficulty of interstellar flight, next slide please, is that to achieve interstellar flight in a time shorter than centuries needs velocities of a significant fraction of the speed of light. But of course, rockets require an amount of reaction mass that's exponential in the speed divided by the exhaust speed. Next slide, please. Well, what's the solution? Well, for 50 years, fusion has been the energy source of the future. And often people add, and always will be. But if we're looking for a power source that's energetic enough for interstellar flight, fusion is the obvious choice. Here is the easiest of the fusion reactions to ignite. Click, please. Perfect fusion would give you an exhaust velocity of about 8.7% of the speed of light. with the caveat that's if everything were perfect. Well, there's a lot of problems with this. One is actually that it takes tritium. Tritium is radioactive. It has a half-life of 13 years. Second, notice that neutron coming out. Well, the neutron actually carries most of the energy, but neutrons can't be directed by electromagnetic fields. Next slide. So it could work, but it's slow. Next slide. With a velocity of 8% of the speed of light, you might get interstellar flight. A mass ratio of 100 would give you 40% of the speed of light. That would mean 99 tons of fuel for each ton of spacecraft weight. Unfortunately, if you want to stop, you have to square that mass ratio. That's a mass ratio of 10,000. And that's if the conversion were perfect. All of the energy of the fusion goes into the exhaust. And the worst problem, we don't even know how to do controlled fusion. Well, so turns out though, next slide, as I talked about in the previous slide, space is not actually empty. It's very close to empty, but it contains interstellar hydrogen, also in fact, interstellar dust, interstellar rocks. Next slide. So in 1960, Bob Bussard asked, do we actually need to carry that reaction mass? Why don't we just use that interstellar hydrogen in the interstellar medium, scoop it up and use it for fuel? Next slide. So this in principle was a rocket that could accelerate forever because it doesn't carry fuel. It scoops it up, and the faster it goes, the more it scoops up. I'll add a spoiler here. Even though the fuel is free, no, you can't keep accelerating forever. Sorry, science fiction writers. And special apologies to Paul Anderson. The faster you go, the more stress on the scoop, and eventually the limit of material strength sets in upper limit. Which brings us to an important point. Next slide. The scoop that gathers the interstellar hydrogen can't be a physical object like this artist's conception. It has to be many kilometers across, and any physical material would be far too heavy. The proposed scoops, next slide, would be electromagnetic fields. So models like this have to be considered just conceptual ideas. The main part of the scoop would be invisible electromagnetic fields. Next slide. It would look perhaps something like this, where the wires are used to produce the current and the charges that make the electric and magnetic fields that channel the ions and bring it into the center to the scoop. Well, what's wrong with that? Next slide. I showed you this slide before. This is how much hydrogen there actually is in the region around the sun. At the time that Bussard wrote his paper, a best guess for the density of interstellar hydrogen was 1 to 2 atoms per cubic centimeter. Most of his calculations are scaled to scoop mass divided by hydrogen density, and he only gave an example calculation at the end of his article where he gave his actual assumptions. For his calculation, he assumed 1,000 protons per cubic centimeter. That is, he was using as an example a ship flying through an interstellar hydrogen cloud. The real numbers turn out to be a lot worse. Depending on which direction we go, the density, hence the acceleration, is either an order of magnitude worse or 1 to 3 orders of magnitude worse, and an astonishing 4 to 6 orders of magnitude worse than the numbers assumed in his example. Next slide. So fuel actually turns out to be the least important of the problems, of the multiple problems. Next slide. The technical problems can basically be categorized, next slide, into 3 categories. I talked about the interstellar hydrogen, less dense than Bussard assumed. Next slide. The next problem is that there's no known or projected fusion method that uses hydrogen, just protons as fuel, and that's what you get in interstellar space. At the center of the sun, we do get proton-proton fusion. I will mention that is at a temperature that gives you thermal X-rays at about 10 to the 20th watts per square meter. And you can't allow any of that energy to escape. But in fact, the idea didn't actually work at all. The idea that you can scoop up interstellar hydrogen was not really more than Bussard's thought experiment. Next slide. Let's see, where am I going next? The next problem is that the fusion must occur in milliseconds as the atoms pass through the throat. That's because you're collecting charged particles. You can't collect the uncharged ones. So when you accelerate charged particles, they emit Bremsstrahlung, so you can't slow them down. If you slow them down, you emit more radiation than you're going to get, and you end up producing a parachute and not an electromagnetic scoop. Turns out, actually, that's a good thing. Ader and Zubrin said, well, let's use that as a parachute. Stopping is also a real problem here, but that's not the problem of the Bussard ramjet. Next slide. Well, I've told you 3 of the many, many reasons that it won't work. So let's now start talking about how do you make it work? Well, actually, Singer and several later authors said, well, wait, instead of carrying the fuel, why don't we just put the fuel in the path? So we don't scoop up the ambient hydrogen, but let's put the fuel on a runway of fuel pellets by a dedicated craft that just goes and drops fuel behind it at predetermined locations. Each one has the fuel and locator beacons, and maybe they have a tiny amount of propulsion to station keep in the predetermined location, or maybe not. Maybe the ship just finds them wherever they are. The late Jordan Kerr, however, sketched out an even better idea. Next slide. He came up with an idea that he called the Bussard buzz bomb. So instead of using the interstellar medium, as Bussard proposed, the fuel is deliberately placed in the path of the spacecraft, as Singer suggested. And each fuel has the locator beacons, and we ingest the pellets with the interstellar probe. Next slide, please. So then his addition to this concept was to use impact fusion. So he pointed out that at the speeds we're going, if we're going to do interstellar flight, nuclear fusion is achieved just at the temperatures produced by impacting 2 things together. So if a small pellet carried on the vehicle impacts a pellet of fusion, the impact releases enough energy to ignite that fusion reaction, producing a large amount of energy. As he pointed out, if you have a trail of these pellets and each one gives you a bang, as you go through that trail of pellets, you're doing a series of successive microexplosions, really literally buzz bomb propulsion. Next slide. There's a number of basic problems here. There's some really hard engineering issues with the fact that at hundreds of kilometers per second, you're going to hit something with an accuracy of possibly fractions of a centimeter, but that's just an engineering problem. I trust the engineers, they can solve things like that. Here are the things we need to know. What is that actual impact fusion threshold? What fuel do we use, and how do you start it, since you can't get fusion until you're already moving at velocities far higher than you can get to with conventional rockets? Next slide. Well, let's start with that question, what's that impact fusion threshold? In his back of the envelope calculations, Jordan said, oh, you can get impact fusion at about 200 kilometers per second. Turns out, doing a literature search, that was quite optimistic. That was assuming the fusion particles are already compressed, perhaps by laser beams. Looking at particles that are not compressed, the target temperature for DT fusion, again, that's the easiest fusion to get, says that you need a thermalized plasma at about 4 kiloelectron volts per particle. That turns out to be a little bit under 700 kilometers per second. Next slide. So instead, we might want to use a different reaction. How about the proton-boron 11 reaction, or aneutronic fusion? Next slide. Well, why pick that one? DT is the easiest reaction to ignite. Boron has a charge 11 times that of a proton. So the Coulomb ignition barrier is 6 times higher. So why do something that's 6 times harder to ignite but has lower energy per unit mass? Well, the first answer is that all of the reaction products are now charged particles. So magnetic nozzles work. But a second thing is that the fuel can be diborane. Next slide. Diborane has the wonderful advantage that it's a liquid at a very slight pressure. Next slide. Here's the reaction. Proton plus boron splits the boron into 3 helium neutrons, giving you 8.7 MeV. The exhaust is charged, allows it to be confined and directed. Next slide. Well, we can do that calculation, but turns out I said it's harder to ignite, but it's harder to ignite thermally. Turns out to be not much harder to ignite by impact fusion because the boron has a charge of +5, a 5 times higher Coulomb barrier, but it's 11 times more massive than hydrogen. So the boron atoms carry 11 times more energy than hydrogen at the same velocity. That means that the impact fusion threshold is very similar to the DT impact fusion threshold. In fact, my back of the envelope calculation is maybe a 20% higher velocity. So more like 700 kilometers per second rather than 600. Well, next slide. Look at the calculation of energy. Here's the energy release. This is the mass. Use E equals mc squared. Next slide. So here's the reaction. You're converting about 1/10 of the rest mass into energy by using the exhaust velocity formula. Okay, we're getting an exhaust velocity of 4.5% of the speed of light. Not too bad. Move on to the next one. Of course, that's if everything's perfect. Okay, so we have a fuel. We know what speed we need. How do we get that? Kerr proposed that we just start it using electromagnetic acceleration, essentially a rail gun of the pellets. That's pretty hard to do. In fact, I think Andrew Higgins is at the conference. He did an analysis of electromagnetic accelerators. I'll defer to him to go into the technical details of why this is really hard, but it is really hard to make an electromagnetic accelerator to shoot something up to 600 or 700 kilometers per second of macroscopic particles. More reasonably, if you have the ship and the pellets each have half the velocity and traveling in opposite directions, you might be able to do this with clever trajectory using conventional means. Next slide. So if we start with a gravitational slingshot, we can drop that pellet dispensing spacecraft into a highly elliptical orbit that drops in very close to the sun and pre-positions the stream of pellets. Then our spacecraft will follow the same orbit around the sun, but in the opposite direction. That gives you that double velocity. Next slide. So the peak velocity, if you had a sun skimming orbit, would be pretty much the solar escape velocity, 617 kilometers per second. So you'd get actually over 1,000 kilometers per second with that head-on velocity. That's comfortably above that 650 kilometers per second impact fusion threshold. You might ask the question, wow, how do you get down really into the inner corona of the sun? But turns out Solar Probe Plus has given us a lot of confidence that we can get in too close to the sun. And there's been quite a few NIAC projects looking at getting even closer to the sun. The trick there is basically very, very reflective materials with high emissivity. So once the reaction would be ignited, the spacecraft would accelerate into the pre-emplaced pellet stream and head out of the solar system. Next slide. So here's the final slide. The bottom line, and this is how you would launch that. You would launch your system from Earth. Before you've launched it, the pellets have already been put in place. You do a Jupiter swing by, gives you a gravity slingshot into that sun grazing orbit. You drop in close to the sun. You hit the pellets that are going 617 kilometers per second in the opposite direction. And then you accelerate right along that runway under fusion power. So maybe Bussard's impossible dream was not so impossible after all. We can get to the stars by collecting fuel along the way. We just have to put the fuel in place before we start. Of course, some engineering details remain. So let's get working on it. Thank you.
Thank you. So first question, how does the architecture and shape of a Bussard buzz bomb spacecraft differ from a Bussard ramjet?
The difference is that, well, the difference is nobody knows how to make a Bussard ramjet, but the main difference is we don't need the scoop because the pellets are small. So we're not trying to grab a whole bunch of diffuse material. We just have tiny little pellets that we need to hit. So it would look like a flying stovepipe. The engine itself would be very little more than just a long pipe with magnetic fields inside to hold on to the plasma once you ignite it. There's actually a beautiful artist conception, but I wasn't sure if I had permission from the artist to use it, so I didn't grab it. I didn't have time to go dig up the artist. But think of it as a flying stovepipe.
Thank you. Here's a question. Isn't most of the mass in the boron which you have to carry?
Yes. Well, doesn't matter which one you carry. And turns out once you have the impact, it doesn't matter whether the boron hit the hydrogen or the hydrogen hit the boron. So you'd have to do some useful calculations as to the optimum ratio. But you carry, the faster you go, the more you can let the boron be emplaced, and the less you have to actually carry. So as you start out, it has to be about 50-50. But as you go faster and faster, you can have more of it in the pellet runway and less of it that you're carrying. But yes, it's true. This is not a zero fuel vehicle. It is a less fuel vehicle.
Thank you.
And I think we're at time. So Jeff, thanks for doing double duty. We appreciate it. And we hope to see you next time in person. Thanks.
I hope to be there in person too. Thank you.
All right. With that, we're on break. Time for caffeine, time for cookies. They should be in the same place as yesterday. We're on schedule, so we'll be right back here in half an hour at 3:20 sharp. Thanks, everybody. Remember to take a look at the tours and to take a look at the Birds of a Feather dinner clipboards at the registration desk. All right, we made a mistake this afternoon. We apparently made the food in the break area too good because there's about 20 people in there eating quesadillas. I just went in there to try to chase them back, and I see a couple coming in. We're going to stay on schedule. We're going to go and get started. Hopefully, we'll chase a couple more people in here at the limit, but we do want to try to stay on track. So next up is David Messerschmidt. David, take it away. Biggest trick is to keep an eye on Zoom.
Motivated by work that we're doing on Starshot that you heard about earlier. I'd like to contrast two different types of missions to illustrate a point. One type of mission is the launch landing type mission where we launch a rocket, accelerate it for some period of time, and then decelerate it and land. And once we've landed, we do scientific data collection and transmission back to Earth, and we get light propagation back. That's one type of mission, and a very different kind of mission is the one that we envision in something like Starshot, which is launching a spacecraft or a probe, we call it. Spacecraft is kind of a little bit optimistic, a probe, which using directed energy acceleration, so we have a short acceleration cycle, then we have a ballistic cruise cycle where the probe is influenced only by gravity. Then we have scientific data collection as the probe passes Alpha Centauri or some other star system. And after that, we transmit the data back while the probe is still in ballistic cruise mode. And so then we have abandonment of the spacecraft at the end of transmission and light propagation back for getting the data back to Earth. The thesis I'm going to talk about is that the requirements of these two different kinds of missions are very different with regard to speed of the probe or the spacecraft. In particular, in the launch landing mission, there's a strong argument for maximizing the speed of the spacecraft. If nothing else, if we have a human crew aboard, then we would like to minimize the elapsed time as measured by a clock on board the spacecraft, the proper time of the spacecraft. And the way to do that is to accelerate as much as possible and for as long as possible, and go, in other words, go as fast as possible. And that's a pretty strong argument. In the case of the flyby mission, I'm now going to argue that we should actually go slower than we can under some circumstances, particularly as we want to increase the amount of data that we get back from the scientific investigation. So the more general thesis, which I believe and I'd like to convince you of, is that we should look at the stakeholders for a mission. We should look at what their wants and needs are, and then we should carefully catalog the assumptions. And when we do that, we may find that, in fact, we don't want to go as fast as we could go. Okay, so in terms of the things, the stakeholders and what they care about, this plot captures that, the assumptions of what I'm going to talk about. First of all, the assumption is that the primary stakeholder is a science investigator who's collecting information in a flyby and wants to get that data from that flyby back to Earth reliably. The thesis is that that investigator cares only about two things, cares about the amount of data you get back and the latency with which you get it back. That is, that time delay until you get the data back. What that investigator does not care about directly is the speed of the probe. And except when you do the flyby, when you're in the vicinity of the target, the science investigation would prefer if the probe was moving more slowly so that you're in that vicinity for a longer period of time. Other than that, the investigator doesn't care about the speed of the probe. So on the horizontal axis, and I'm going to repeat this plot about 5 or 6 times, so it's important to understand the axes. because these are the two metrics which I believe are important to the science investigator. One is on the horizontal axis is the total received energy on Earth that the probe is able to get back to Earth. And this is a relative measure here. The absolute depends upon a lot of factors like aperture sizes and the electrical power available in the probe and so forth. This is a relative axis. The total received energy reaching Earth, the way communications works, is proportional to the total volume of data that we can get back. So this is a stand-in, an easy way to think about the amount of data that we can get back. So we are going over, this is a log scale, and we're going over 8 orders of magnitude on this horizontal axis, which would be equivalent to the difference between getting back 10 bits and 1 gigabit of data. On the vertical axis, we have the data latency in years over a period from 0 to 100 years or 1 century. The data latency is defined as the time elapsed from the time the probe is launched until the data is received back. And it's important that you appreciate that I'm defining latency in terms of the complete return of data, not some initial return of data. The reason I think that's important in this particular instance is that we're going to operate under extremes of energy efficiency. And so under those conditions, I think it's the case that we will not be able to recover any of the data until we have the complete transmission back from the spacecraft in hand. That is, we don't get any data without getting all of the data. Okay, so with those two definitions in mind, and those are the two metrics that we're going to work with, there is a feasibility region, a region where it's possible to receive the data back with certain latency and a certain data volume. That region has a lower boundary, which I call the efficient frontier. The efficient frontier is where we actually want to operate if we're doing the best job we can for the science investigator, because at the efficient frontier, we get the lowest latency possible for a given energy back to Earth, or alternatively, we get the maximum energy for a given latency. And if we operate inside the feasibility region away from the efficient frontier, then we're not doing our best for the science investigator. Okay, so the first question you ask is, how can we operate on the efficient frontier? What variables do we modify in particular to move from the left to right? You could imagine that there'll be different requirements for different probes, that we're launching different probes with the same infrastructure on Earth, and there will be different requirements for different probes. And two extremes might be, for example, the very first probe that we launch is an engineering evaluation as to whether the probe technology is working. And in that case, we want that evaluation information to come back as soon as feasible. And we do not have high expectations for the amount of data we're getting back. It's simply some minimal telemetry data like A's working, B's working, C's working, everything survived the interstellar medium. As far as we know, we would be able to collect data if we had the appropriate equipment on board. On the other hand, later in the evolution of the system, we could imagine that there's some much more complex instrumentation that requires large amounts of data coming back. And so we'd like to operate far to the right, and we would accept the larger latency that's inevitable if we get larger amounts of data back. Okay, so what happens if we take a single probe with a single mass and speed? In a moment, I'm going to vary the mass and speed. So right now we're holding mass and speed constant. How do we move through this feasible region? Well, the variable that we can modify very easily is the transmission time after encounter, the time until we suspend transmission. Obviously, if we transmit longer, we'll get more data back. So that's one variable we can play with. So what I'm doing here is varying the transmission time after encounter, and we get a curve like this. This curve only touches the efficient frontier at one point. So it is capable of achieving one point on the efficient frontier, but it's not capable of achieving any point on the efficient frontier to meet the varying needs of different probes. To the left of the tangent point to the efficient frontier, this particular strategy has a larger latency than is possible, that is feasible. The reason for that is the time to target. The low latency is lower bounded by the time it takes the probe to reach the target. To the right of the tangent point of the efficient frontier, the probe is unable to get back nearly as much data as is possible. And the reason for that is distance squared loss. The loss decreases with distance as the probe is moving away from us after encounter, and that places an upper bound on the total amount of data that we can get back. And in particular, it keeps us from getting anywhere near the efficient frontier in terms of data volume or energy. Energy is what we're plotting here. So if we want to get different points on the efficient frontier, the way to do that is to vary the mass and speed of the probe. And so I've shown here 4 cases where the probe has a unit mass, where the probe has a mass 10 times greater, 30 times greater, and 100 times greater than the nominal 1 unit mass unit. Now, when we move to higher mass, the probe slows down. And we'll talk about what that mechanism is in a moment. But the curve moves up and it moves to the right. And the tangent point to the efficient frontier moves as we make that modification. So the way to achieve different points on the efficient frontier is not through varying the transmission time, but it's through varying the mass and speed of the probe. And in particular, if we want to get more data back, we should slow down the probe and increase its mass. Now let's talk about, so larger mass, lower speed as we move to the right, higher data volumes. Let's talk about what the mechanisms are for these curves to move up and to the right. For the curve to move up, the reason for that is as we increase the mass of the probe, we reduce its speed. And in fact, the latency increases as the quarter power of the mass. Now, if we assume that we have a fixed launcher, which is launching many probes, and the only thing that's varying among the probes is their mass, then we would kind of expect that the latency would increase to the square root of mass because it would be constant kinetic energy. Constant kinetic energy would correspond to a speed that's proportional to the mass to the minus 1/4, I'm sorry, 1 over the square root. It's actually much more favorable than that. If we assume that we're operating in a diffraction limited launching mechanism, we have a fixed beam, a fixed size of beamer. And as we increase the mass, we can increase the size of the sail. If we increase the size of the sail, we can also increase the acceleration time and thereby increase the kinetic energy that we impart to the probe. And so that's why it goes up as a quarter power. The curves move to the right, and the reason for that is has to do with the 1 over distance squared loss that we were talking about earlier. As the loss goes down as 1 distance squared, then we can we suffer less loss over time if the probe is moving slower, and we can also we hypothesize we can also increase the transmit power of the probe because we can increase the electrical power. We have more mass to work with for electric generation. We can increase the aperture area for the transmit aperture. And so together, those two things suggest that the transmit power goes up as a square of the mass. So those are the two mechanisms that allow us further to the right, go further to the right. Now, what we notice is that for these different curves, the tangent point to the efficient frontier, which is actually the lower envelope of all these curves, that point is about the same point in the trajectory at the transition between latency limit and energy limit. So it's not surprising that there's a consistency for different mass probes. In particular, I've shown the curve of the transmission time equal to 10% of the travel time. And as we vary the travel time due to changes in speed, the transmission time is 10% of that. And that falls very close to the efficient frontier. The other curves I've shown are 1%, 50%, and 100% of travel time.
David, you're about 3-minute warning, and we got some questions coming in, just so you know.
Okay, thank you. Just one more point. It is important to recognize that we are exchanging higher launch energy for larger energy back to Earth because we are accelerating the probe for a longer period of time. It turns out that that trade-off has large efficiencies of scale, as indicated by this equation here. So the takeaways, the time to increase the received energy or data volume, we should slow the probe. The slower probe also benefits scientific data collection, so that's good. Higher mass probe is easier to design and fabricate, arguably, and efficiency. To achieve the maximum efficiency, we should have a transmission time that's consistently about 10% of the travel time under the assumptions that we've laid out. And with that, I'd be happy to answer any questions.
Thank you. We've got a couple of questions. The first question is, if you decrease speed and increase mass, what happens to cost? If you decrease speed and increase mass, what happens to cost?
Well, we're actually decreasing speed by increasing mass, and the main impact on cost is that the beamer infrastructure doesn't change. We're assuming that's fixed. However, we are going to be accelerating the spacecraft longer in order to get lower speed and higher mass. And so there is a cost in terms of increased energy consumption in the launcher. That does, however, obey economies of scale.
Okay, one more question. Do you include anything like Moore's law for technology development on the efficiency for transmitting data versus mass? For example, delaying launch to develop technology?
Well, no, I don't believe there is a Moore's law for transmission. There are, of course, innovations that can be made at the physical layer, such as quantum entanglement and things of that sort that are being investigated. But if we use a conventional style of optical communication, such as NASA's using in their interplanetary system that's going up, if we use those kind of conventional approaches, which is what we've assumed here, we're operating very close to theoretical limits. So there's no additional efficiencies to be had there. But that affects basically the ratio of received energy, which is what I emphasize here, to the number of bits. That ratio is affected by the efficiency of the communication. Unfortunately, there's no magic bullets for making that more efficient.
Thank you.
David, thanks very much. Appreciate it. Thank you. Okay, for I believe what's going to be the first time today, I'm not swapping between an in-person and a Zoom call. So Jessica's going to swap out the cover on the microphone. We were concerned that Andrew Higgins would be trapped by the American immigration system, but you braved that barricade and made it through. So Andrew, take it away. Thanks.
Seabirds such as albatrosses and remote control gliders use a technique called dynamic soaring that enables them to go much, much faster than the wind through which they're flying. Today, we're going to present a concept for how we might be able to perform this maneuver in the solar wind. So to give you some background on this work actually evolved out of the last two TVIW meetings. In Huntsville in 2017, Jeff Grayson gave a talk where he evangelized, that was his words at the time, a concept called the plasma magnet, which was proposed by John Slaw at the University of Washington, Seattle. So what the plasma magnet is it's a magnetic sail of very, very large extent that is generated by a very small size and very low power coil. And what it allows you to do is have that sail be accelerated by the solar wind at accelerations up to 1 meter per second squared. Now, as originally proposed, this is a purely drag device. It can only drag you up to the speed of the solar wind. But at the next TVIW in Wichita 2017, Jeff Grayson proposed an idea that lets you drive into the wind. Now it uses the plasma magnet, but now you stroke the plasma magnet through the wind blowing over the vehicle. And as the solar wind acts, or the blowing wind acts on the plasma magnet, you can extract power from the wind blowing over the vehicle. And then you can use that power to launch a reaction mass on board. So this is the so-called Q drive. Again, reaction drive powered by external dynamic pressure. Well, at Wichita, we had a lot of discussion, and that led to a collaboration between our group at McGill University and Jeff, thinking about other ways we can extract power from the wind blowing over a vehicle, but not use reaction mass on board, but rather use reaction mass, again, in the solar wind. So the concept we're going to talk about today is to extract power as the wind blows over the vehicle, then use that power to launch solar wind transverse in a perpendicular direction, delta Vy, which will create a lift force upward, okay? And because that flow has a lower velocity, we can accelerate it more efficiently. So you actually get a greater force downward than you get in drag from the power extraction, okay? A force downward pushing up is lift, and the lift can be greater than the drag. In other words, an L on D, a lift to drag ratio greater than 1. And that is the key to enable the dynamic soaring technique. So the back history on this is when we got into this, Adam Crowell pointed out to us that in Paul Birch's paper on dynamic compression members from JBIZ in 1989, there's about a 1-paragraph discussion of this entire idea. So that actually anticipated much of our work. Well, what is dynamic soaring? So in this schematic, you're seeing an albatross going about 15 meters a second in quiescent air, traveling through a shear layer into wind blowing at 5 meters a second. So now relative to the wind, the albatross is moving at 20 meters a second. It now turns 180 degrees and still going at 20 meters a second because there's very low drag. It re-enters the initial air, but now it's gained another 5 meters a second because it was riding on the wind. In the lower air, it now does another 180-degree loop and comes back and re-enters the upper layer again. Every time it does this maneuver, it gains twice the velocity of the wind. So every time it gains 10 meters a second as it does this loop. Okay, this was first noted by Leonardo da Vinci. You can notice the backwards writing, so you know who wrote these initial sketches where this technique was noted. So now remote control glider pilots do this. I don't have time to play the video. The glider moves so fast in this video, you almost can't see it. But this is where the gliders that are just launched by hand, no onboard propulsion, are now able to get up to speeds of almost 900 kilometers an hour by doing dynamic soaring in the wind blowing over the top of a mountain. Well, it turns out even before albatrosses and glider pilots figured this out, the universe figured this out. So this is actually how we believe galactic cosmic rays are generated by shock waves from, example, supernova. So charged particles bouncing back and forth between either side of the shock wave, like a tennis ball bouncing back and forth between two approaching trains, gets multiplied in velocity with every elastic bounce off the media. Okay, it's more complicated than that, but at some level, it's the same thing as the albatross, which is elastically bouncing off the wind that it's flying into. So where might we apply this technique in the solar system? Where are there sources of shear that we can exploit? Well, one is the solar wind. So in the equatorial regions of the solar wind leaving the sun, the wind is 400 kilometers a second. But as you move to higher latitudes, the wind speeds can be 700 to 1,000 kilometers a second. So there's a delta V there of 300 or 400 kilometers a second we might explore it. As we go in the heliosphere, there's a feature called the termination shock. And we know about this because Voyager 1 and Voyager 2 flew through it. And in the little plot on the upper right, you'll see the velocity measurements of the solar wind dropping from about 300 kilometers a second down to about 150 kilometers a second. So again, there's a delta V there, which we can exploit for this dynamic soaring technique. But how is this actually going to be done? So I'm going to turn this over to my colleague, Matthias Lauruturu, who will explain to you the actual analysis and the concept for the spacecraft.
Okay, so how do you do it? Well, the first thing, the big question is how do you do it in space? And the first thing you need is to start acting like a wing. And to do this, let's consider that you have a spacecraft moving through a medium at speed v wind. You can, as we just said, extract energy in the wind direction. This is the delta Vx. And with that energy extraction, there's a drag associated to it. And you can use that power that you just extracted to accelerate the medium in the perpendicular direction. This is the delta Vy. And again, there's a lift associated to it. And overall, you've decelerated the medium in the wind direction, accelerated it perpendicularly. You're starting to act like a wing. And there's a very important parameter for any wing. It's its lift to drag ratio. And you can do the math. It comes back to this expression where you have the lift to drag ratio is essentially 2 times the speed of the wind divided by delta Vy. And this is very interesting for us because as delta Vy gets to 0, well, the lift to drag ratio becomes arbitrarily large. And with high lift to drag ratio, you can start doing incredible things. We cannot quite get a delta Vy that is extremely close to 0, but we can get it low enough to do very interesting thing. Yeah, so that equation, there's 1,000 ways to sit. There's 1,000 ways to derive it, but essentially there's 2 links that you can make. The first one being with the hypersonic wing flat plate model. Or you can consider that you have 2 rotors operating perpendicularly to each other, one acting like a windmill, the other one acting like a rotor. And all of those links and all the different ways that you can derive this expression all showcase different physics. But in the end, you end up with the same expression. So if we have a high lift to drag ratio, the next question is, okay, well, what is the analytical model of dynamic soaring? How fast can we get? How simple is it to do it? And you can do very simple models. So first, let's consider that we're traveling roughly at constant wind speed u. And for simplicity, we'll say, okay, we'll follow circular trajectory. And at the interface, we cross the interface at constant angle alpha. If you go through the math, this is the energy transfer equation between the wind and the wing. You can equate the losses and the gains due to drag and the dynamic soaring maneuver. This is the final equation you have. If you take the limit of that equation when you're just glancing at the interface, when alpha essentially tends to 0, you get that expression. And again, you can understand really easily why a high lift to drag ratio is very interesting. So the expression is the difference in wind speed divided by 2 times the lift to drag ratio. So now you can also see why having a low delta Vy is very interesting for us. So it's a simple analytical model is very interesting, but how good is that model? You can essentially compare that model to numerical simulations. The equation of motion is quite trivial. By adding a few constants and saying, okay, the acceleration from drag is roughly 1.1 meters per second squared. We'll take a lift to drag ratio of 25. We'll show later that it's a very conservative value. But in the end, this is the trajectory that you follow. I assure you, those are circular trajectories. They're just very stretched out. And you can compare the theoretical model in blue to the numerical simulation in red. And what you have is that the theoretical model matches within 5%. For something you can derive on the napkin, it's not too bad. So yeah, so let's talk about how do we produce that lift? What are the requirements we have? I don't have to explain to you, we need high efficiencies like most of the interstellar technologies. But the main issue here is the extremely diffuse medium. We have a very fluffy wind, and you can talk about it in very different ways. You can, from our dynamic standpoint, you can talk about low platform loading, low ballistic coefficient, low parasitic drag. It all boils down to a very diffuse medium. And the main point is physical wind do not meet those requirements. They are just, yeah, they do not meet them. But as Gillen showed in his article, plasma waves are extremely promising. So let's take a look at them. So first of all, waves carry momentum. Quite stupid, but we just have to say it. The energy flux associated with a plasma wave is defined as the Poynting vector, which is the cross product between the electric field and the magnetic field associated with the plasma wave. The momentum flux is also simple to derive. It's the energy divided by the characteristic velocity or the velocity of energy flow. In the case of the in the case of pure EM radiation, you just end up that the momentum of a photon is its energy divided by the speed of light. But we have plasma waves, and in that case, the characteristic velocity, the velocity of energy flow, is the group velocity of the wave. And so you get that very neat expression that the force that you can get by launching a plasma wave with a Poynting vector S and a group velocity Vg, you get that the force that you have is the area of the wave launched by the antenna times the Poynting vector divided by the group velocity. So the main question here is how low can we get that Vg? Because let's just go back. That force is the lifting force. So we want that force to be as high as possible, and we want that Vg to be as low as possible. So yeah, so one of the waves that we're interested in is the Whistler wave. There are thousands more waves that are interesting, but we'll just take one example here. The Whistler wave, so now the value we're looking for is the group velocity. There's different theory you can call to get the group velocity of the Whistler wave in the interstellar and solar wind. But essentially, there's two that work very well, the warm plasma theory or the Vaslov hot plasma theory. We took the warm plasma theory. What you can get is that at 1 AU, you have a group velocity of 100 kilometers per second that gives you a lift to drag ratio of 15. At the termination shock, where we're interested to do dynamic soaring, you can get, and that's a very conservative number, again, 30 kilometers per second for the group velocity. That gives you a lift to drag ratio of 50. And the last point we have to talk about when it comes to technological requirements is that those wavelengths that we're talking about are on the kilometer size. So we do not want an antenna in the kilometer size. So we have to find compact antenna design that are able to produce unidirectional waves. In fact, they already exist. This very simple double loop, those two knotted loops are able to produce unidirectional wave. You can see the wave packet in the positive X direction has a much higher energy than the one in the negative X direction. So when it comes to the vehicle, let's just first take a mechanical analogy. Let's imagine that we have a boat and we want to act as a wing on the surface of a lake. This is not a paddle wheel. Even if it looks like this is not a paddle wheel, this is a water wheel for power extraction. So this produces drag. With that power, we can agitate a paddle and send waves on the surface of the lake. And that will produce lift, that will push the boat in the top left direction. So how do we do it? Well, for now, in our case, we're considering as the energy extraction mechanism, a plasma magnet array, where you stroke the solar wind, as we just explained. You have the storage ring in the middle, and you get the energy out of it. And for us, that's an interesting technology because it has a constant drag force and it has a large area of interaction. Then we have at the bottom the plasma antenna, which is able to launch plasma waves in one direction. The mission, again, is roughly simple. You use the plasma magnet, which is a drag device, to simply get you up to wind speed. Once you're up to wind speed, you use dynamic soaring on the termination shock or the fast and slow solar wind. In the case of the termination shock, you can reach 2% of C in 1.6 years. Yeah, so the conclusion are roughly simple. A high lift to drag ratio is possible in space plasma. And to produce that lift, plasma waves near plasma resonance are quite a good technology and seem like a nice implementation. And by using that high lift to drag ratio, 2% of C in 1.6 years through dynamic soaring is reachable. Thank you. Yeah, that's good.
Maybe you both answer questions, so.
Thank you both. And let me start reading the question while Andrew's walking up. First question, the centripetal force at your final velocity is 2.4 meters per second squared versus your 0.1 meters per second squared drag. How does this affect your analysis?
Can you repeat the question?
Surely. The centripetal force at your final velocity is 2.4 meters per second squared versus your 0.1 meter per second squared drag. How does this affect your analysis?
This does not change anything because the centripetal acceleration is the lift force, not the drag force. So the lift force will be your lift to drag ratio times 0.1 meters per second squared. So this does not change anything except I misunderstood the question. Okay.
Okay. Next question. Would you repeat the albatross process in succession at the plasma shear boundary for interstellar travel?
You want to answer?
I mean, the easiest way to think of it is the albatross is bouncing off a moving wall. And if you have a moving wall, a train or a truck coming towards you, you throw a tennis ball, it bounces off that moving surface, it will gain twice the velocity of that moving surface every time. And if you have a shear layer between different regions of solar wind, you see the same effect. You have a slower region, a faster region. And as you fly back and forth between those two regions, you're effectively bouncing back and forth off either of them. And then shock waves as well. There's a supersonic flow coming in, subsonic flow leaving, and you're essentially bouncing off those two walls moving at different speeds. And every time you do that, there's an opportunity to gain velocity.
Thank you.
Yeah, is that it? I think we're set. All right. Thanks, guys. We appreciate it. Our first tag team. I used to think that describing somebody as a grand old man of a particular field was a compliment. I'm getting old enough, I'm not sure that's true. But Louis Friedman has been everywhere, done everything. He, among many other accomplishments, was the founder of the Planetary Society. If you're not a member, you should be. And come on up, we're going to check you out on your slides. And Louis is going to talk to us about visiting an exoplanet. So, forward, back, that's all there is to it.
Yeah. Okay. Thank you. I don't know if I like being the grand old man.
I'm not either.
It's happening a lot lately, so I'll accept it. Actually, I've spent my whole working career in the solar system. And to be specific, I've spent it in planetary missions. And did that go on? Next slide. So I've spent a whole in planetary missions. What makes planetary missions special is the search for life. That's the key question that dominates people's interest in space and dominates really this, why we even have a space program. We want to know if we're alone in the universe. We want to know what is the origin and nature of life. And even if we're alone, we want to know what the conditions for life are. So it's a driving factor is searching for life. I think that's also the driving factor in everything we want to know about exoplanets. And even though this group, and we tend here to be focusing on the engineering of interstellar exploration, we want to not lose sight of the fact that the driving force behind that, the reason we're doing that is to really look for life in the solar system. Now, there's lots of life in the solar system, probably. We don't know that yet. We haven't discovered any besides on our own planet, but there are exoplanets. And on the exoplanets, we now know there are billions of exoplanets. We know there are a large percentage of them, or some percentage of them, are in a habitable zone. Many are Earth-like in their size. Some are Earth-like in their temperatures. And we know a lot from the studies of life here on Earth that life exists in lots of extreme environments. So we're optimistic about the idea of finding life in the universe. And exoplanets in particular, with so many to look at, there's a tremendous push to be exploring exoplanets. And that's exactly what my talk is going to be about, which is the idea of trying to explore exoplanets. But it's a difficult job. If we take a look at an exoplanet from any telescope on Earth, it's 1 pixel. It's not even 1 pixel. And we can't do better than that. Any telescope that we could build in any practical sense still can't image an exoplanet. It would still be less than 1 pixel of the distance is too great. We would like to get up closer than that, but no, to do that, in the solar system, we're stuck with the lambda over d limitation of telescopes. I can't see the slide there, but the idea of limiting ourselves with telescopes, can we get there? And that's what I'm going to talk about next. There are really 2 ways of getting there. One is the idea of really getting there with interstellar probes, and the idea of and that is just at the present time a bridge too far. We know now, and we've heard it many times here, that the only method that is actually being worked on as practical is that we have to get our energy outside from an external energy source, either and from sunlight or beamed energy. We have to have beamed energy to make it. This is the work of Bob Forward that really many years ago made that the notion of practical interstellar flight. And of course, it's been carried on by Phil Lubin. And now Breakthrough Foundation, Breakthrough Initiatives is really doing developmental work on that idea. So it's an exciting idea that we can get there, but even in that idea, it's very technology limited. With the most practical thing that they think of is they're hoping to get to the nearest star with 1 gram in 20 years. Now that's only the nearest star, and that means only 1 exoplanet or maybe a couple at that star. And they're not the most, if you look at the survey of habitable exoplanets, they're not necessarily the most interesting ones. We want to survey lots of exoplanets. We, being the community, would like to survey lots of exoplanets. We'd like to explore exoplanets, find out conditions of habitability as they vary, and also conditions of what are the most possible ones to look at. So the idea is that to reach an exoplanet, we need to we can't, it's a bridge too far for now, and maybe with all of the things we've been hearing about, it'll be something of the future. But for now, something else comes to the rescue, and that's the idea of virtually exploring exoplanets. We can virtually explore exoplanets because nature comes to the rescue to overcome that telescope limitation that I mentioned by having a solar gravity lens that magnifies whatever it's looking at by 100 billion times, by a factor of 10 to the 11th. That means using the solar gravity lens, we could not merely see an exoplanet, we could resolve surface features on an exoplanet. We could see forests, we could see seas and lakes, and if we're lucky enough, we could see cities. The idea that if we could use the solar gravity lens as a telescope, that would give us the ability to see exoplanets. And it's not distance limited. We could see exoplanets 10 light years away, 50 light years away, 100 light years away. And in that region, there are at least a dozen candidates of potentially habitable exoplanets, possibilities for life. Now, not all of these are we going to see life, but even as we learn from the varying conditions, we'll be doing comparative studies to see the conditions for life, and it'll be the most important result we can get. So we're highly motivated to do it. So all we have to do is use that nature telescope. Problem is, it's pretty far away. It's 550 AU is where it begins. And the solar gravity lens, which I think this audience is familiar with. Let me see if I can move this. The solar gravity lens begins at 550 AU. It's formed by the fact that light rays, when they go by the sun, are bent, and as they go varying distance by the sun, they're bent at different angles, and they form a locus of points starting at 550 AU out to infinity, basically. And so we have to not just get to the focal point. Fortunately, it's a focal line because we couldn't stop there if we got there. We want to fly down that focal line and do the imaging as we fly down the focal line. The solar gravity lens, say, is 550 AU. That's a tall order. We've never gone in the solar system past 140 AU. That's where Voyager is. So this would be further than we've ever gotten. And on this chart, it looks like it's halfway between here and Alpha Centauri, but this is a logarithmic scale. And those are factors of 10 in distances between the way. And in fact, it's really only 1/500th of the way to Alpha Centauri. So compared to interstellar flight, it's a very short distance away, but it's still longer than any place we've ever gone. And it's an engineering challenge to get that far. But if we can get that far, what we do is we use this bending of light rays to form the focal line, and we take an Earth-like planet and we would see it not as an image in a square, like an image like you're used to seeing in a photograph, like we do with planetary spacecraft. When we get images of the planets, the image gets constructed in what's known as the Einstein ring around the focal line. And the Einstein ring basically has to be sampled pixel by pixel to reconstruct the image. So you end up getting a convoluted image, which is the one in the left there. And then when it's deconvoluted, you'll end up with the image of the exoplanet. And it's very much now this work, which is being done by Slava Turyashev at JPL. He's now gone through all the simulations necessary, including even accounting for the sun's oblateness and all the factors that could perturb that imaging process. It takes integration time to do the deconvolving. But you will spend your time on the focal line doing that deconvolving and producing the images of the exoplanets. I should point out that in a system like TRAPPIST, which has several potentially habitable exoplanets, you could jump from focal line to focal line while you're maneuvering down on a single mission and see multiple planets, sort of like as if you were orbiting Jupiter and going from multiple moons to see it. But if you want to see planets around different stars, you have to have different missions, because then you would be going to a totally different geometric region, totally different focal line. The concept we've come up with to do this is a solar sailing mission to reach the exoplanet. Why solar sailing? Well, the advantage is, first of all, any other technique to get out there in a reasonable mission lifetime, the goal being to get out to 600 AU and 20 AU per year, for example, in less than 30 years, you'd have to use nuclear and that's not on the horizon now. Nobody's even working on developing that. Or you'd have to use a chemical rocket that would go like 2 solar radii from the sun with a giant heat shield. And that's a massive launch vehicle problem as well as a technology problem that for massive. So when thinking big, you would go nuclear or try to do something like that. The opposite is to think small. A small sat and a solar sail can go to say 0.2 AU or 0.15 AU, still close to the sun, but nowhere near as close as those distances, and pick up the necessary speed to get out at 20 AU per year. We've come up with a different sail design. This has been led by Explore, a private company that's working on this with Lagarde, who has got a solar sail experience. And they took the sun vanes that were on the Lagarde Sunjammer spacecraft and made this new spacecraft design all vanes, basically multiple sails. This gives the ability to package it on a small set much simpler, because now each of the sails is smaller. They can be they don't have to be deployed and unfurled in the same fashion. You can get more area to mass in an easier packaging volume. In addition, you get a lot of control capability from the individual vanes, and so it gives you a more flexible control design, especially if you're trying to achieve multiple objectives as you fly in toward the sun to pick up your speed, and then outward to go to your exit the solar system. So the basic mission concept is shown here, where because it's a solar sail, you don't need to get a large launch vehicle. In fact, you could ride share up to high Earth orbit or to C3 = 0, and then spiral in toward the sun using the sail to tack in toward the sun. And then as you get to perihelion, you turn the sail and you pick up all your solar power. And if you are, and depending on the distance, there are 3 important factors: distance, perihelion, the area of the sail, and the mass of the spacecraft. And I'll show that on the next slide. But depending on that, you can achieve speeds as high as 20 AU per year or even higher in advanced designs. So this shows the trade-offs, and and basically you want as large an area as possible to catch sunlight and solar photon energy. You want the mass as small as possible because it's proportional to area to mass as small as possible, so that the momentum from the photons goes into velocity. And you want the perihelion to be as low as possible so that you can get maximum sunlight power. And you see on the graph here, the perihelion distance is actually the key, is the factor you should work on the hardest. Sure, you can get your area to mass. Right now, the current solar sail, the 2 successful solar sails that are flying, Light Sail, which is done by the Planetary Society, has an area to mass ratio of about 8, and Icaro's had an even lower area to mass ratio. To get up to 100 or 200 is going to take real advantage of the small sat design and larger sail deployments, and that's why we went to that other configuration. But you can do your area to mass ratio increases, and our current design right now for a test mission we're looking at is somewhere in around the 50 to 60 range. But if you can get your perihelion distance, you see that with getting close to the sun, like 10 solar radii, you will get an enormous increase on that. And now people are working on sail materials that can do that. Ordinary CP1 or Kapton certainly will allow you to get to 0.2 AU, and that's good enough for the current kind of missions. But in the future, we'd like to get even closer and get the so that we can get the higher exit speeds. So right now we're working on a technology test mission, not the full mission that would go out to the solar gravity lens focus. As I've indicated, that's taking technology development to get the area to mass ratio as high as possible and to do these sail materials that will get close, as well as to fly the interplanetary small sat, which has not yet been done. But we want to prove that concept in a much smaller mission, one that would only exit the solar system at 5 to 6 AU per year. Now I say only, that's still about twice Voyager speed and would be the fastest spacecraft ever if we can get this launched in a few years, like we hope to, because it's basically a rather small, simple small sat design, and the prototype is actually being built right now. And so this mission is probably affordable at low cost, and it would still have the ability to exit the solar system fast. Our technology test mission idea is we would only pay attention to it for a year. We don't intend to do an interstellar mission or into the interstellar medium on a test flight. But if we can prove the whole concept of flying close to the sun and outward, we will have proved the basic concept of the mission design. The next step up from doing a technology test mission is to improve upon these parameters, put a science payload on it, and maybe even rendezvous with an interstellar object. This design is capable of rendezvousing with, we could, by going in close to the sun, as you see there in the diagram, you could actually park in a solar circular orbit and wait for that interstellar object to be discovered. And then when it's discovered, just optimize your sail trajectory to rendezvous with it. You could rendezvous with it before it got out to Jupiter or Saturn's orbit. And you could even, if you have the right parameters and depending on the speeds involved and everything, for the Borisov mission, we actually showed that we could rendezvous with it and land on it. And so it offers a lot of promise. Now that would be a future technology step. The initial goal is to do the technology test mission, then to do some solar system mission like the interstellar object rendezvous, and then move out to do the solar gravity lens focus. At that point, we will have proved not only will we be imaging exoplanets, but this is sort of a precursor to the ideas of interstellar thinking. They'll all be developed at the same time. We'll be able to pick the habitable planet candidates. We'll be able to know a lot more about them because we'll be imaging them, and we will have proven the basic concept of get smaller and smaller interplanetary satellites and sails as the propulsion mechanism. So thank you. That's it.
Thank you. We have one question.
Only one?
The only one that I find that didn't get answered by your presentation before I could ask it. If we had a constellation of telescopes orbiting at 2 AU functioning as an interferometer, what would be the resolving capacity in the visible spectrum or infrared? And is it even possible to do this?
Well, I'm not the person to answer that question. I know that it is being studied as a thing. You still wouldn't be able to get the image of the surface features, but of course you would be getting a lot of information and certainly the spectroscopic information, the thing. But I can't give you the detailed answer on that constellation of telescopes. The basic size of the lambda over d limitation, that basic size gives you a scale of a telescope that has to be many kilometers in diameter. If you try to achieve that with a constellation of telescopes, you can do that kind of thing, but you're not going. You'd have to make them work all together as a phased array, and of course that hasn't even been done here on Earth to that extent.
Thank you.
Questions?
No more questions.
Yeah, no more.
Louis, thanks very much. We appreciate it. Thank you. That's great. Thanks. Appreciate it. All right. Last but not least, we've had a busy day. We're going to finish up with a Zoom call. Chris Lembach from Texas wanted to be here and Are you in Texas or are you in California? Where are you, Chris?
Texas A&M
Yeah, it's
University.
Texas. I
in
saw
College
that
Station.
Stanford. Yeah, I saw that Stanford logo in the top left. I thought he was from Texas. So anyhow, Chris is on the Zoom call and is going to take us down with particle beams. Thanks.
All right. Yeah. Thank you very much. I just want to say thank you to the organizers for allowing me to cap off a wonderful afternoon of talks. I've been very interested in all the previous presentations and also to give me the opportunity to present over Zoom. I would have much preferred to have been there in person. I'm a Wildcat, as is my wife, also an Aggie now, of course, but former Wildcat, and I had been looking forward to coming back to Tucson, but I'll have to catch it next time around. So today I'll be talking about a propulsion concept that we've been looking at here at Texas A&M and also with my collaborators at Stanford for about 3 years now through a combination of NIAC Phase 1 and Phase 2 grants. So here at Texas A&M, myself, my group, Hayden Morgan, who's a master's student, Rohan and William Hodges, our undergraduates who've been working on the experimental part of the project, and then our collaborators at Stanford, Ken Hara, and his group have been looking at simulation, some of which I'll show you today. And so we've been looking at this combined laser and neutral particle beam concept, and today I'll be talking about some of the key phenomenology that we've been researching and have discovered through the last few years, and how these two beams are interacting with one another. Next slide. And so for the first part of my talk, I'll introduce the basic phenomenology of our concept, and then the second part, talk about some of the recent simulation results. Next slide. And so as you know, the title describes, this propulsion concept is a combination concept. So there have been some previous work in this area. I know that Jordan Kerr had some concepts related to using laser propulsion and then using that to propel spacecraft, light sails, which then accelerated other spacecraft. But really, we're looking at combining two beam approaches that have been talked about, you know, throughout this conference. One, photonic propulsion. So we're utilizing the momentum of the laser field itself, and then particle beam propulsion. And there's been a number of works looking at everything from droplets to plasma beams to neutral particle beams. And so what we want to do with our concept is really combine the two. So combine a laser and a neutral atomic beam. So it's not plasma, it's just neutral particles, just like the air in this room. And combine them in such a way that we're able to leverage an interaction. And really the central part of what we're looking at is trying to develop an interaction between these two beams, which will give us some interesting physics, which we can use to improve the propulsion capability. So it's not a linear, you know, overlap, but really we're trying to tailor an interaction which allows us to do more in terms of our propulsion capability. Next slide. And so the genesis of this, by the way, was really inspired by some of the work on laser propulsion, in particular the breakthrough Starshot, and really about, you know, 2017 timeframe. I was kind of thinking about, you know, something I had recently read on it, and I was thinking to myself, wow, you know, the real issue, or one of the real issues, is diffraction, right? So that's why you need these huge laser arrays. It's why the light craft needs to have such a large, you know, collection area. But what if we didn't have diffraction, right? So what if you didn't need a large transmitter array, or your spacecraft didn't have to be, you know, large itself, and you could just, you know, keep pushing on the spacecraft with the beam for a very long time, right? So that would eliminate many of the constraints that we currently have on the size, weight, and power of the whole system. And so that was really the genesis. And of course, in vacuum, you know, there's not too much we can do about diffraction. It's going to happen. Nature does not like gradients of anything, and will seek to eliminate them. And that's true, by the way, not only for laser beams, but also particle beams. So there's thermal motion associated with the particles that we're sending into vacuum, and they spread out. And so the A and B pictures here kind of show that as the spacecraft goes farther away, those beams spread out and you capture less and less momentum as you get farther away. And what we'd like to do is, again, engineer this interaction that will eliminate or mitigate diffraction and allow you to use a smaller transmitter and be able to have a well-defined collimated or focused beam with which to propel a spacecraft. And if we can achieve this, We have several advantages that are shown on the upper right. Another one is that you get somewhat better thrust to power ratio using particles as opposed to photons in terms of the propulsion. Of course, there's many challenges, and we've been working to address those through our phase 1 and phase 2 NIAC projects. Next slide. And so with this type of propulsion architecture, the mission looks like this. Please click about 5 times. Yeah, so you start with an acceleration phase, and just like laser-based propulsion, the acceleration phase for an interstellar mission is going to be on the order of about an hour or so, over which the spacecraft travels about half an AU. And then most of the mission is the interstellar cruise phase, and then a short flyby and transmission. And there's been really interesting talks today about each of those different phases. And so what we're trying to do is focus on the physics and the dynamics of that acceleration phase and how these two overlap beams are going to interact with one another as they go out through the interplanetary medium, and trying to understand what kind of parameters do we need these beams to have in order to have this mutual interaction. And I'll be talking about 2 key phenomena. One is optical guiding. So we want to use the particles like a waveguide, an extended macroscopic optical waveguide. And then the other piece of this is the optical forces, which are generated by the laser beam and interact with the particles in some way in order to keep them from spreading out into the vacuum of space. And so we've been focused primarily on developing a physical model, so a simulation capability for this process, as well as looking at stability, which I'll talk about today. How stable is this to perturbations? Next slide. So phenomenology, how does this concept work? Next slide. So one of those key effects, which I just mentioned, is refraction. And I think many of you are familiar with this. Certainly when I was a student in Tucson, there were many hot days where I observed scintillation. I can't say I saw a mirage myself, but I think many of you are familiar with this. Certainly in Texas, I see it a lot. When thermal perturbations are present, right, the density of the air changes, the refractive index changes, and so you get optical phenomena as seen here in the jet exhaust. This also works for other fluids, by the way. So there's a great display here, the picture on the left, of a company that sells basically light shows. So you have a LED which injects light into a very uniform laminar stream of water, and you can see that illuminated. And so there's a lot of precedent for having changes in flow density, right, result in the guiding or refraction of light. And for the concept we're looking at, we actually need to look at very rarefied density. So we're not talking about a lot of mass that's sent out in the atomic beam, and yet we're able to guide light. And one example of that is some recent simulations done for atomic clouds. So these are very low density, 10 to the 12 per cubic centimeter. That's about 6 order of magnitude below atmospheric density. And you're able to see these very strong guiding, and you can actually have anti-guiding or kind of an expansion of the beam rather than a guiding effect. And this is all because we can exploit resonant phenomena of the atoms that we're looking at. So in this case, it was rubidium atoms. And so in order to quantify how strong that interaction is, we've been using this characteristic parameter, the V number, common in fiber optics, which is basically a measure of how strong is the refraction compared to the diffraction. And if the V number is of order 1 or more, that says that there's enough refractive effect to keep the light from spreading out, and it can be guided through the atomic beam, right? So this is a gaseous beam of neutral atoms. Next slide. The other key phenomena is this optical forces, and these were made famous in the 80s and are commonly used for confining atoms in cold atom experiments, looking at fundamental ultra low temperature physics. We're talking about microkelvin, millikelvin, and it turns out that there's forces when you overlay a laser field with the atomic atoms themselves. There are forces which develop, which either pull the atom toward or away from the high intensity regions of the laser beam. Click really quick. And so that shows just a little simulation of what it would look like. So the atoms want to come toward the high intensity part of the beam. And again, there's a key parameter which we need to take into account when we're thinking of how strong this interaction is going to be. It's essentially the depth of the potential from which the forces can be derived relative to the thermal energy scale. And as long as that potential is deep enough relative to KT, the atoms are going to be strongly affected by the laser, and we can effectively trap them and prevent them from expanding out into vacuum. And there's been some previous work back in the 70s actually showing you can do this with atomic beams. And so this is from a paper showing that when you overlay a laser and sodium beam, you can actually see an intensification of the atoms as they're being channeled toward the high intensity part of the laser beam. Next slide. So we've been looking recently at the dynamical interaction, right? So you have these two systems interacting with one another. They're essentially overleaved with one another. And so how are they going to interact, and what kind of physics do we expect to result from that? There's been some great work looking at cold atoms in the lab. So this is stationary atoms, but having the fundamental physics, which I just mentioned. So you have a laser propagating through those cold atoms that produces a phase modulation, so refraction of the laser. After some distance, you back reflect that back to the cold atoms, and this produces an intensity modulation, which the atoms then respond to. And so there's a key feedback loop there between the laser propagation and the atomic motion. And what has been found, this is some work out of Laborie, and they've shown is that you can see this very interesting spontaneous pattern generation. This is a hexagonal pattern which is formed due to that interaction. So the atoms come to some equilibrium distribution, and so the laser as well. And you get this interesting dynamics, and there's a critical threshold, like a spatial threshold for when the system will become unstable. And we wanted to apply the same analysis to our particle beam. Next slide. And so we've gone through, unfortunately, something went wrong in the transfer here. But suffice it to say, the figures are messed up, but we performed this analysis, and this was really motivated in part by some comments made, I think, at the last TVIW by Gerald Jackson, who said, we should do the stability analysis. It's not as trivial as, like the two-stream instability with a Poisson equation, but nonetheless, this motivated us to actually go and do this analysis, and out popped another key parameter, which is related to the dynamical interaction of the laser and the particle beam system. This is this parameter tau. And let's see if you go to the next slide, what happens. Oh yeah, okay. So all the figures are messed up, but so this parameter tau is actually really important because it tells us something about how the atoms in the laser beam are going to affect each other. So as this feedback loop keeps going, diffraction, and then the motion of the particles, and then more diffraction, how's that going to happen? Well, it depends on whether the relative angles between the thermal motion of the particles, kind of the thermal spreading, and the diffraction of the particles. And what we found, which was really quite interesting, and you can't really see it from this figure, is that there's a wave number, so a particular spatial scale, where at higher frequencies, you can actually damp the motion or the disturbance which is introduced into the system. And so what this figure is supposed to show is that when we introduce a disturbance in the field, in the laser beam, it actually becomes damped. And the mechanism by which it becomes damped is that you end up having a series of resonant particles which are traveling in certain preferred directions, basically when tau is equal to 1 here. And those resonant particles are able to kind of take that perturbation and the entropy of that perturbation and put it into the kinetic distribution function, so the velocity distribution of the particles. So we have a upcoming PhysRev A paper on this, which has the correctly formatted figures. So please take a look at that. Next slide. And so moving forward, so this is a really interesting result, right? That there's actually a mechanism out there which can act to stabilize the beam and damp out any perturbations in that intensity profile we might have. Next slide. So moving on to the capability, I'm going to go through this quickly. We did some calculations for our phase 1, which showed that we really can potentially achieve up to the kilogram level payloads for an interstellar mission on the order of 0.075 C or 7.5% C. The capability scales very strongly with the final velocity. So we actually get a big benefit from going just a little bit slower. And we wanted to see, well, this is based on those key phenomena I mentioned earlier. What happens when we actually simulate the dynamic interaction of these two beams? Next slide. And so we built a physical model. Let's just including all the phenomena I just mentioned. Next slide. And we wanted to look at the coupled propagation. So can we, by combining these two beams, create a self-guiding effect which allows us to propagate them farther than diffraction alone would allow them to? Next slide. And so this is some work, of preliminary work out of the group at Stanford, Ken Haro's group. And what they did is they built this simulation capability and injected two Gaussian initial profiles, so a Gaussian spatial profile, and then varied the density of the atoms. And as you vary the density of the atomic beam, this basically sweeps through a range of this V number. So it changes the ratio of refraction to diffraction as these beams co-propagate. And what they found is quite interesting, that there's actually an optimum density or an optimum V number with which to co-propagate these two beams. And that's close to what's known as the critical density, which gives us a V squared of about 2.4. And so at this distance, we get, as you can see, we get very long distance propagation. This is many diffraction lengths. But as you go to very much higher density, that increases the refractive effect, and you end up getting a pinching effect which occurs. So you kind of focus down much faster than you want to. And what this does is it transfers a lot of energy and kinetic energy to the particles, which are then ejected. And so there's a mechanism that's at work here, which is a dynamical heating. It's the interaction between the two beams which heats the particles and ejects them. And if we can what this shows is that if we can minimize that dynamical heating, then we can potentially get farther and farther distance propagation. Next slide. So I think I need to wrap up and give some time for questions, but the next step is we've actually built a capability to determine particular profiles of the intensity and atomic density, which allow us to minimize the dynamical heating. And that is our next step, is to use those as the initial condition to propagate further. Next slide. And so this is the summary, and I'm going to leave it there and allow the audience to ask any questions. Thank you. I'll have to get the correct version of those slides, the correct rendering for the final final PDFs which are sent out.
Thank you, Chris.
You also, it's a paper by October 1st. You can get the right figures in the paper.
Exactly. There we go.
I have a couple of questions here, which I'm going to combine because they're kind of similar. Can we use this laser particle beam approach for interstellar comms? And are there any weapons applications for this technology? Both of these, I think, have to go with range before decollimation.
Sure. Yeah. I mean, so the comms, I thought a little bit about the communications, because there's a lot of interesting things that could be done with communications. I think the real issue would be that number one thing to consider is that you are using some mass, right? So the total amount of atomic mass that you need to actually do the whole mission is something on the order of maybe 10 kilograms, which actually isn't that much when you think about it. But if you're communicating for a very long time, that's 10 kilograms is for the hour of acceleration. If you're communicating for a very long time, you may end up needing a lot of mass. So that's kind of the number one thing to think about. And then the second concern would be basically centrifugal force. So if you're in the solar system, you have to worry about all of the forces from the many bodies that make up the solar system, right? So as you send out your combined beam, if there's reference frame effects, as you're trying to point somewhere, you may end up having those beams kind of curve off to the side, right? And that in turn provides an additional consideration on what those parameters need to be to avoid basically decoupling the atomic beam from the laser beam, because of course the photons are traveling at the speed of light and the atoms are traveling at something less than that, and so that's another consideration. Oh, and then the weapons. So I think it was maybe a year or so ago that Mike Griffin, in his capacity, decided to de-emphasize long-term development of kind of particle-based weapons in space, and to my knowledge, that has not changed. But if anyone knows that it has, please let me know.
Thank you. And one more question. Does the Landau damping mechanism create a dynamic radial aperture that causes particle and photon loss at the radial edges of the two beams?
Yeah, that's a great question, and I'd be interested to know the answer. So the analysis we've done so far has been basically a plane wave as the baseline state. And so we haven't done the analysis with axisymmetric beam because we just haven't gotten to that yet, and we have to input the profiles actually that I showed, the stationary profiles for the laser and atomic beam, and do the stability analysis around those profiles. So we haven't done that yet. I think it would be interesting to look at that going forward, but it's something that should help answer that question that was asked.
Thank you very much.
Okay, Chris, thank you. Appreciate it. That was great. We look forward to seeing you in person next time. So thank you.
Me too. Thank you.
All right, a few housekeeping details. That's it for the plenary sessions today. If you look at the calendar, we're at 4:40, which is right on time, which means we're about 2/3 of the way through the day. There's still a lot left. So, but this is the end of the plenary sessions. We're going to let you leave the room. Maybe go out and get some sunshine now the rain has stopped. Enjoy some of the pretty afternoon. Someone had mentioned the organizers. I do want to emphasize that all of the organizers of this, with the exception of our incredible AV crew back there. First off, by the way, thank you, AV crew. Thank you. Applause. Because doing a hybrid meeting like this is non-trivial. There's an awful lot of equipment back there and a lot of brain power making this work as smoothly as you've seen it. But for everything else, this is a volunteer run organization. And to say thank you to our volunteers, we're actually having a reception for them in about 15 minutes over in the copper room. So if any of you want to go by and say thanks to the volunteers, I will start that by saying thank you, volunteers, because we literally could not have done this without all of you. So thank you. A couple more details. We're not feeding you tonight. There's 22 restaurants within 3 blocks of here, so there's lots of choices. If you are formally or informally putting together a birds of a feather dinner, clipboards out at the front desk, pull people together that you want to meet with, that you want to talk to. You can make that happen on your own. The clipboards at the front desk for the tours, we're going to take those up in about 15 minutes. So if you're going to want to go on one of the tours tomorrow, sign up and pay in the next 15 minutes because we got to figure out how many buses we need because buses cost money. So we got to close that down. Back in this room, as soon as we leave, they're going to remove this podium, put up a table. We're going to have a author panel at 6 o'clock. Many of the authors are in the room. But these are science fiction, science facts, and science history authors right here.
Stephen, will that be Zoomed?
I believe so. Charlie, that's going to be on Zoom, right? Yeah, that will be Zoomed. So the same Zoom connection for everything else will work for that. So you can watch that. That is sponsored by Bain Books. We hope to have a drop-in Zoom appearance by Tony Weisskopf, publisher of Bain. If not, I'll channel Tony. I know how to do that. But that will be from 6 to whenever the panel runs out of steam. But we will also do a book signing after that by the authors whose books we are going to be able to have in the lobby at the sales table, which should be being set up right now. And that will end at about 8. And that will give you time, even if you attend the whole thing, to grab a quick dinner and be back for the working tracks at 9 o'clock. We'll put the wall up again and have the 2 working tracks. No, excuse me. Tonight, one of the working tracks is here and one of the working tracks is in Copper Room. That should be on your agenda. And if not, it should be. Anyhow, so we'll be set up for that. Lots of fun left to have, but thanks for sitting with us for the whole day. If the sun has gone out, it's pretty outside, get some sunshine, and we'll see you back here at 6 o'clock for the author panel. Thanks, everybody.